So first of all, respected speakers, dear colleagues, the students, ladies and gentlemen, it is my pleasure to welcome all of you in this event, which is organized from the chemistry department, KFUPM, and KFUPM Institute for Knowledge Sharing, abbreviated as KICS. The topic for our today forum is Chemistry for Sustainable Energy. I am Nawaz Tahir, a faculty member at Chemistry Department, KFUPM, and I will be moderating this forum and will be throughout with you. As the title reflects, the main agenda of our discussion, of our thoughts, will be to benefit from our respected speakers' research experience, thoughts, to highlight and to learn the role of chemistry for sustainable energy. As you can also see from the videos, we have 4 very much distinguished guest speakers. Of course, I will introduce officially later, but I'm sure it's really pleasure for us that probably we don't need to even introduce, they are world fame already. So the format of this forum will be, after this short introduction from my side, then we have Professor Abdulaziz Al-Sadi, the Dean of College of Chemicals and Materials, KFUPM, with us. So I will request him to officially open the forum, and he will share his opening thoughts. Plus, he will also give us a brief introduction about the chemistry department, KFUPM. We will each, like the presentations, we will have a Q&A session, like question and answer sessions at the end of each presentation, starting by the keynote speaker, and then followed, we have 2 sessions. First session is about energy conversion, and the second will be about energy storage devices. So at the end of each presentation, there will be a question and answer session. From the audience, you have the option to ask question either raising your hand, or you can also type your question in the chat window, and on your behalf, I will ask this question, I will forward this question to the speaker, and you will get your answer. So at the end of the forum, we have again 10 minutes of a panelist discussion, and that will be a kind of conclusive remarks or an outlook about the agenda. So first of all, I would like to request Professor Abdulaziz Al-Sadi, the Dean of College of Chemicals and Materials, to open the forum officially and share your opening remarks and a brief introduction about the chemistry department. So Professor Abdulaziz Sadi, it's over to you. You can share your screen, and we are happy to have you here. Thank you.
Thank you very much, Dr. Tahir. Assalamu alaikum all. Good afternoon for those who are in afternoon, good morning. I'm not sure about the time zones of our respected speakers, but I am sure that we are happy to have them with us today in this interesting forum. Thank you, Professor Grätzel, Professor Ahmad, Professor Nair, and Professor Ruffo for being with us today. And also thank you for all our attendees today. I am a chemist. Yes, I am the Dean of the college, but I'm a chemist. I came from the chemistry department. And I have a strong emotion towards my department anyway. I have to say that. And I'm happy to see the department today organizing a forum touching a very important topic, which is sustainable energy. And as important that topic for the department is important also for the college, which is the College of Chemicals and Materials. And this is a recently reformed college at KFUPM. Maybe you are aware that King Fahd University of Petroleum and Minerals went through a a major reform in the past 2 years, and the academic sector went also through some reorganizations of the department and the colleges. And one of the outcome of such a process was our college, which is College of Chemicals and Materials, that hosts 4 departments that used not to be together before for 40 years. Now they are together. And those departments are the chemistry, chemical engineering, material science and engineering, and the 4th is the bioengineering. So the college focus a lot on the materials of sustainability and how we can serve that theme from our background that goes through materials to chemicals to bio. And we are building the expertise and the capabilities towards that mission. The chemistry department is one of the leading departments at KFUPM in terms of research. We have excellent number of faculty members who are publishing high quality research in different areas. And I think such a forum is a reflection of the quality of what the department is doing by attracting top-notch speakers from different areas and different parts of the world. So I don't want to take a lot of time, and I will let the floor be with Dr. Tahir to start the presentations. I know that our attendees are waiting to hear from our distinguished speakers today. And I wish you today all the best. And I thank you again. I thank again our distinguished speakers for taking time from their busy schedule to share with us their thoughts and recent scientific outcome from their groups and labs. And thank you for our faculty and our speakers who are with us today. Yes, thank you, Dr. Tahir.
Okay. So thank you very much, Professor Abdulaziz, for your thoughtful opening remarks and also highlighting the emotions for chemistry department. Of course, we are happy being a chemistry faculty members, and we see that. So now the next, it is my immense pleasure to really announce our keynote speaker, and it's honor more than pleasure, because I went to many meetings where I was in the attendees sitting in the back of the halls and waiting for Professor Michael Grätzel's talk. And today I'm going to announce his name. So it's really my pleasure. I think he doesn't need an introduction for sure, because in the science field, particularly in chemistry, he has more than 1,800 scientific publications and 360,000 more than that citations. So almost he is one of the leading highly cited chemist and material scientist. And moreover, his inventions, like now, they are part of our textbooks. So I think if I will start reading the list of his awards and honors, I am certain that time will be only my limit. There are more than 15 different countries. This is just, I'm just telling, very conservatively, because I'm sure the list is very long. And most of these countries have awarded multiple times their awards to Professor Michael Grätzel. All leading research organizations, when I look in the list, all research are chemistry societies. So they have awarded multiple times these awards and honors to Professor Michael Grätzel. The Kingdom of Saudi Arabia, the highest scientific award, King Faisal Scientific International Award, he received in 2015. And I have also I have also really honored that I was also present in the audience when Professor Michael Grätzel received in 2011 Gutenberg Award and Max Planck Institute for Polymer Research, Mainz, Germany. So this list is really long. As I already said, if I will go into that list, so probably we will be just, we will not have a time in this forum to have, his thoughts and his research. So thank you very much, Professor Michael Grätzel, for joining. And I will leave the floor to you. It's over to you. And we are happy to hear from you today for your talk, which is about molecular and perovskite photovoltaics for producing electricity and fuels from sunlight. So please, over to you, and floor is yours. Thank you.
Thank you, Taya. It's a great honor to be here. And wow, you gave me really a splendid presentation. And I feel very humble to be the first speaker here and honored. I'd like to also thank Dean Abdulaziz for his kind words. So without further ado, I will share the screen. And let me see. Yeah. Hello?
Yes, Professor Grätzel, we can hear you.
Yeah, so yeah, let's try this one more time.
Please
I go on
your
share screen. Yeah, that's what I did. Okay, now let's see. Okay. Okay, let's try this one here. Okay.
Yes, we can see your screen now.
Okay. Now I'm. Okay.
Thank you.
So, yeah, so can you see my screen now?
Yes, yes, we can see.
Okay. So the lecture which I will give you today deals with our research on the conversion of sunlight to electricity and also to chemical fuels. Actually, I started out as a researcher that worked on the hydrogen generation from sunlight. I felt that, hydrogen was a very attractive vector, and it's coming back. I mean, as the hydrogen car is developing. And so that's many, many years ago when I was a young postdoc in the United States. I became infatuated with the idea to make hydrogen from sunlight and water. But then in the 80s, the funding in solar fuels was very poor. So just to survive, I thought, well, maybe we should also think about electricity production, which is a more straightforward application of sunlight. And so that led us to the discovery of mesoscopic solar cells. And yeah, and today I will cover both areas, okay? So our inspiration comes actually from the natural system, which is a molecular-based photoconversion system. So as chemists, we're thinking in terms of molecules, and I'm a chemist too. And so I was intrigued, even during my studies, how nature manages this challenging reaction, turning CO2 into sugar. And so the light reaction in particular is a light-driven electron transfer involving chlorophyll molecules. And so it's a molecular photovoltaic really. And so we tried, our inspiration came from that molecular system. And yeah, from that inspiration evolved, yeah, the photoelectrochemical cells. Here we have an example that was many, many years later. This is a tandem of iron oxide performing water oxidation under visible light to oxygen. And this is coupled to a perovskite cells that just adds driving force for the hydrogen generation. So it's a water splitting system. So finally we managed to build systems that would split water with visible light. But really what took off at the same time is the dye-sensitized solar cell based on sensitization of mesoscopic titanium. Titanium oxide is a large bandgap semiconductor, and everybody tried to shift the light response into the visible, and so did we. And so we used sensitization, which at the time when we started was decried as being a hopeless enterprise. And so, but everybody worked on those flat electrodes and didn't think about going to the nano dimension. That was our contribution. We came up with this nanoparticulate electrodes. That wasn't by coincidence. We had worked we were the first to work on colloidal semiconductors and studied, just curiosity-driven research, studied their properties. And so, yeah, so the dye-sensitized cells then evolved, and today we have applications like the green panel here, which is a dye-sensitized solar cells in a car. Yeah, it's electricity, solar electricity for electric cars, recharging station. But also what turned out to be an extremely important evolution was the advent of perovskite solar cells, which really have taken off and still very much increasing the both the efficiency, stability, and so yearly output now 8,000 research papers in perovskite solar cells. And so we were very happy that the dye-sensitized cell gave birth to this perovskite first sensitized, and then the sensitizer became a compact film. But still today we are using the most efficient cells, still use a nanocrystalline electron selective contact. And so, yeah, so this gives you the journey we went through, and now let's get going on my lecture. And so first I want to talk to you about our inspiration and research approach. Sometimes young people ask me, well, how did you come up with this idea, and did it happen overnight? And one thing is, well, it is extremely important to be highly motivated. If you're not highly motivated for your research, then I think you will not perform well. And so yeah, so out of this inspiration and our research approach, which was to go to the nano dimension and the molecular sensitization, came out the molecular photovoltaic field and quantum dot sensitized, dye-sensitized solar cells. And then this led, as I said, to this rise of perovskite. And finally, today we can make fuels from sunlight. And for example, we can split water with just using a perovskite silicon tandem with 18% efficiency, the hydrogen and oxygen. And we can also turn CO2 into ethylene. And I remember one time we had a Gordon conference Gordon Research Conference in China, and the chairman of Aramco was talking, and he said, if you want to do something useful, make ethylene out of CO2. And that's exactly what has happened. Today, the ethylene can be produced electrochemically from CO2 with Faraday efficiencies over 80%. And so I'll talk a little bit about this at the end of my lecture. But that has become one of our main research directions. If you're now going to fuels derived from CO2, this is more challenging than just do the water splitting. So yeah, I think I don't have to dwell on the issues with environmental pollution and the greenhouse effect. So you're all aware of this. It's a severe climate issue and environmental pollution issue. And so we all also agree we have to keep the CO2 level down in the atmosphere. And so to maintain the temperature rise below 2 degrees, that's the Paris Agreement. And what you look at here is is an analysis that Shell published on the internet. It's called Sky Scenario, and Shell is an oil company, so they're not biased. They see the future in terms of reducing dependence on fossil and increasing renewables. And and so according to this scenario, in a nutshell, the photovoltaics has to grow by about a factor of 200. It's very easy to understand. Today, photovoltaics, what is the installation we have in photovoltaics? It's about 700 gigawatts. That's the total installed capacity of photovoltaics. But this is peak power. They only produce 100 gigawatt power on the average, because they are day and night. You can understand the seasonal variation and so on. So 700 is really, in reality, it's only 100 gigawatt. And so the consumption today is 18 terawatts. So we are way below 1%, if you think about the ratio. And but the photovoltaic should grow to 32%. And the cake itself, the pie is growing. And so that means that's a factor of 200 to make an impact. That will not cover everything. That's just to make an impact. And so, yeah, and so the photovoltaics has been growing. I mean, we have to admit this is very impressive and mainly silicon based. And here's here we see the distribution, and the left chart is how things should evolve. Okay, but as I said, today we are about 700. This is the point that I'm now just pointing out to you. That's the total installed power, 700 gigawatt, and gigawatt peak. That's peak power, and that's on the left. The blue numbers are yearly installation. That's 140 gigawatt peak, and per year, and hopefully this will go up. It has to go up, but can silicon do it alone? Well, some people have some questions on that, and you see below why there are questions. For example, on the terawatt scale, there is the margins are not very high for silicon, and to increase a factor of 200 is huge investment. And then there's also the large carbon footprint, and there's issues which make people believe that we need to go even to new technologies. Not that silicon will disappear, but new technologies are needed to meet the challenges. And so yeah, let's look at the nature. Well, nature. How much is the power that nature generates in terms of if I take the photovoltaic, the conversion reaction, the CO2 fixation in sugar, and I calculate how much is fixed in terms of CO2 and what's the free energy of combustion, and then I can bring, I average this per time, and then I get 95 terawatts. So that's at least 4 times as much as our present total world energy consumption. So molecules can do it. Okay, that's a molecular system, and well, you know, all the molecule that is the light absorber, and so yeah, and so our approach. I don't want to go too much into the dye-sensitized cells because I have a lot of things to cover today, and so but. In a nutshell, what our approach was to use these nanocrystal arrays, and these are the electron accepting contact for the absorber. The absorber is a molecular absorber. and it has an anchoring group which binds it to the surface of the oxide TiO2. That's by self-assembly, by molecular self-assembly. So it's a self-limiting process. Once you have made a monolayer, it will stop. But the reason why we need these nanostructured films is that if you would do this on a flat surface, you would get hardly any power conversion. It would be the efficiencies are extremely low, below 0.1%. I mean, efficiency of solar to electric conversion. And so there are various reasons for that. And light absorption is one thing. Monolayer doesn't absorb a lot of light, but there are other reasons. And so fortunately, it turns out that this approach is the right one to get the light absorbed and also collect the carriers. Because you might have questions if you have a dye absorbed on one of those nanoparticles and say it injects after excitation an electron in the TI2. So what happens to this electron? Can you collect it over, say, several micron distance? So some people were very skeptical about this approach. And when we first found these extremely high currents with these systems, photocurrents, they asked us to show proof. And for a while I was traveling with my own solar cells and showed the folks it was true. So it's a sensitized nanocrystal that is the light harvesting species in those films. And the cell itself is shown here. So we have those sensitized nanocrystals. Electrons are selectively collected from the dye, from the excited state of the dye. And then they travel to the transparent conducting glass contact. And then in the external circuit where they are doing work, and then you have to bring them back to the sensitizer. Otherwise, you would deplete the sensitizer. And so you need some shuttle that could be a redox electrolyte or some hole conductor to get those electrons back to the dye. And so it's a simple device. School children can make it, and they can use natural dyes like from raspberries or tea, hibiscus tea, to run to make a solar cell. And so our paper, there was one of the papers that was a key paper published in 1991 was this paper Nature, and yeah, it has over 32,000 citations and became one of the highest cited research of all times. It's amongst the 100 most highly cited papers in the whole field of science. So we're very proud of that. Yeah, why was that? Why did we get so many citations? Well, it was the first time that somebody would go away from the concept of having a p-n junction, like the silicon cells, a p-n junction, solid state junction, flat monocrystalline. This is a disordered system like the natural one, and it's based on a molecular absorber. And it is the concept of mesoscopic junctions was the first time pronounced. And so, yeah. And so here's Brian, the author of this paper, myself at a conference in Uppsala some time ago. And today we have a lot of chemistry going on. I don't want to go into details, but the most successful sensitizers, we started with ruthenium complexes, but and they are now commercially applied, I should say. But the research goes towards these donor acceptor dyes that where the donor is, say, the furthest away from the surface, and then under light electrons travel from top to bottom. That's the charge transfer excitation, and then they're injected in the TI2. So you have to have a good anchoring that provides good, coupling between the acceptor orbitals and the TI2, the d orbitals, titanium d orbitals. There's also a variant with a chromophore. We are in the middle of this side donor acceptor system. You have a chromophore. For example, this is a green porphyrin. You have the donor on the left. You can see that here. That's the chromophore. The acceptor is this triple bond phenyl carboxylate. And this dye has been become quite famous was a joint paper we published in Science with the groups of Professor Yi and Eric Yao that are now in that they live in Taiwan. And so today, I mean, these efficiencies have gone up to about 15%, but we're using these donor acceptor dyes now. And also the patent, thousands of patents in this area, not by us. It would be too expensive to maintain cover. But this, our first patent was filed actually in 1988 in Switzerland. And then it became a US patent in 1990. And so, yeah, and here are you see some of the application of those green panels. I already showed you the car charging station. There's some other, the barrier, motor barriers, or also in a house, the balustrades. There's various applications. And we have also a conference center in Lausanne where some of the panels are made of dye-sensitized solar cells. And very recently, we came up with a real good sensitizer. I like to give credit to my graduate student, Marko Stojanovic, who came up with that structure, very simple donor acceptor structure, and can be made in a one batch reaction. And it got this very high photovoltage of 1.24 volts. That's amazing because that would be about double the amount the voltage we would get usually from the ruthenium dyes. And here's Marco again. And you can tell it's the COVID time because he has his mask on. But this dye solution is about to make the sensitizer. And this work was published in Nature Communications recently. And we could show that with these cells, they were particularly successful in ambient light, where they would beat the competitors like gallium arsenide or amorphous ambient light harvesting. And that has become a major industrial effort now. And so cells are being made and sold that harvest ambient light and make electricity and portable electronics. One company that is very good at that is Ricoh in Japan, and it just came out with a new version of the sensitizer. I mentioned also another big company, Exeter in Sweden. They just raised 100 million to build another production plant in Sweden. And yeah, so when you look at this, it's a tape cutting ceremony that was I think 10 years ago in Stockholm. And here's Henrik, and this person is the Swedish king, and Giovanni Fini. So the king himself took an interest in this particular venture. And so they have been very successful in, for example, powering e-readers. And these are solar cells. They have a special technology called powerful technology. And so, yeah, they have now products out on the market like this earphone. They're all self-powered, and you don't need to have a battery to recharge batteries after they have run out. So this has become one of the dye sensitizers that they found applications in those glass panels and these products are the ambient light harvesting IoT application. Now let's go to the perovskites. And yeah, the perovskites are pigments that yeah, have been known for a long time, and they have an ABX3 formula. So A is a cation that is a charge compensating cation, doesn't have any redox activity, and it has to fit into the octahedral geometry, and only certain radii are suitable to make perovskites. There's a Goldschmidt rule that defines those. So yeah, you can almost tell if you select those three ABX whether they would make a perovskite or not from the atomic size point of view. And so yeah, they have this very strong light absorption. They have a lot of lot of strong features, and all of this forebodes well for photovoltaic applications. And yeah, as I said, they emerged from the dye sensitized. Initially, the perovskite solar cell was an electrolyte containing cell, and the perovskite was these nanoparticles. See these black dots? These are perovskite nanoparticles. And Professor Miyazaki in Japan, he came up with this idea to replace the dye by these pigments. And yeah, that was, then Nambu Park came a little bit later. He's a colleague from Korea. And during that time, nobody cared about these publications. Why? Well, the system was not very efficient, about 3%. And it was quite unstable because the perovskite dissolved in the ionic electrolyte. But then the whole thing took off with the advent of solid state versions, the perovskite solar cell. And if you look at the history, here's the dye sensitized, okay? And well, you know, this point was, this statistics there is not from today. So September 2021, so there wasn't much published in 2022. But anyway, the DSC still runs about 1,000 papers a year. But the perovskites, they have really taken off. They go 8,000 publications a year now. So that's a boom, one can say. And efficiencies took off. Today we have efficiencies of over 25%, 25.7% is the certified efficiency. And so almost a factor of 10 up in the starting value. And yeah, and here on the left, you can see the typical cross-section of the perovskites. These are the so-called NIP version, where the N means the electron collecting negative electrode. Is the negative electrode is the Ti2 here, and still mesoscopic, the same we had used for the DSC. And light comes in through this contact, okay, the N contact. So it's called the NIP. And so we have the mesoscopic contact that is an electron selective, as it was for the molecular system. And but then you fill up the pores, and you have a capping layer that is becoming now the main light absorber. This is this bulky part you can see here. And so yeah, so and then there's a hole collector. You need a hole selective contact. In other words, a contact that selectively collects positive charges, and that you need some kind of back collector, which is gold. That could be carbon. There are many options, and so all this is only about say 1 micron maximum thick. Compare this to a silicon cell that is 250 microns thick. So you use 250 times less material. Okay, so and this can be made by solution processing at low temperatures, and you get over 25%, which beats the polycrystalline silicon, not the crystalline yet. Crystalline silicon record is 26.7%, but the polycrystalline is already beaten, and there are some new results where over 26% have been reached, but not certified yet. So yeah, all this started with the solid state, where the electrolyte was replaced by a hole conductor, an organic hole conductor, a p-type conductor, and so by coincidence, two groups published in 2012 these two papers. That's exactly 10 years ago. They're celebrating 10 years of perovskite solid-state perovskite solar cell history. And yeah, so very similar efficiencies. We exceeded 9%, they were slightly over 10. So yeah, but the approach was the same. That is in a way that the sensitizer is now contacted by this organic Hall conductor, which is a triarylamine type molecule, and it's called spiromeotite. So this actually was developed first for dye-sensitized solar cells, and there's a Nature paper we published in 1998 for Professor Udo Bach as the first author. He was my graduate student at that time. He's now a professor in Monash University. And yeah, so this has now become the most widely employed Hall conductor because it matches so well, not only for DS, the dye-sensitized liquid cell, as a replacement for the electrolyte, but also for perovskites. And today's record cells, the ones that get, say, to 25.7%, we are still using this so-called spiral Hall conductor. And so, yeah, I want to also share with you the good news that the rank prize this year goes to 7 people, okay? And 6 of those 7 are on the 2 papers I just showed you as co-authors. And yeah, and the only person who was not on it is Dr. Sok. He's professor in Korea. He came a little bit later with his papers. And so, yeah, so, yeah, going back to the perovskites, you can see the compositional complexity. You have a lot of choices for the anion, the central cation, and the A cation, but not all choices are suitable for visible light. You want to use iodide or iodide bromide mixtures, and you want to use yeah, lead. Both lead and tin are being used. The tin cells are now reaching 15%. The lead cells are still ahead of the tin cells. And so, but there's very active research in the tin field because people want to have an option to change from lead system to lead-free systems. And so, yeah, there's also these 2D structures. And so if you use a large cation in like alkyl ammonium surfactant, then you make a 2D structure, and they have played a role as a protective overlayer in the recent development of perovskite solar cells. And so a lot of people focus now on, excuse me, on the form armidinium lead iodide, which, take this down here, which is the preferred actually material. It's optoelectronically superior to both metal ammonium and cesium, but it has a big problem. It's not stable at room temperature. The black phase is reverting to a yellow phase, a hexagonal phase, and that is not active at all photovoltaically. On the contrary, it kind of, if you have the yellow phase, it will actually decrease the efficiency of the device by promoting recombination of carriers. And so, yeah, so a lot of people focusing now on this phase. For single junction, that's certainly the best choice you can make. And so, yeah, so we were one of the first groups to be able, or the first group to stabilize it by just adding some methyl ammonium cation to the form armidinium. That work was published in 8 years ago, and Professor Meyer being at the Max Planck Institute in Stuttgart and Dr. Norman Pellet was a joint PhD student between the two of us, Professor Meyer and myself. And yeah, and then also then the cesium also is it's an amazing observation. You take cesium lead iodide. It's a yellow substance at room temperature. The former meridinium also, the stable form is yellow, but then you mix them, you grind them in a mortar, and you find the black powder is formed by mechanochemical synthesis, and that's amazing. How that clean reaction, and so we were involved also in this research. And yeah, today let me say a few words about the leading research. Today, a lot of people focus on the passivation layers. You see that the following issue is being faced. You have the perovskite itself is the ionic crystal, very polar, dissolves in polar solvents and in water, for example, and then you have the whole conductor, which is not polar at all, and so so this interface is they need a surfactant to match the two polarities, and so you put this passivation layer in between the whole transporting layer. See here, this blue part is the passivation layer. That's a molecular layer that kind of matches the polarity of the perovskite with the whole transporting layer. And so what do you choose? Well, your chemical intuition has to give you the inspiration there. You have an infinite number of choices, and so chemistry knows no limit. Okay, and so but I just give you some two examples now. One is this thiophene molecule. It's a good passivator. The sulfur will bind with lead, coordinatively unsaturated lead on the surface, and the carboxylates also, and so they also hydrogen bond with some of the A cations. So this turned out to be a very good passivator. You can see that here in the photovoltaic performance. We have the typical photocurrent voltage curves, the so-called JV curve, and this is the IBC incident photon to current conversion efficiency. So get over 90% of incident photon converted to electric current, and so these cells reach 25 milliamps, which is a high photocurrent, and close to 1.51. So high voltage, high current, good fill factor. So efficiencies are high, and we don't want to go too much into the physics here, but one characteristic for a good photovoltaic is that it shows a photoluminescence. So, for example, the cell which we had without the passivator has only a 0.5% quantum efficiency for photoluminescence, and if you put the passivator, it goes up to 2.5 times. That's a lot, and it tells you that you would get a lot more voltage out with a passivator, and you do. You can see the voltage goes up here. It looks like a small increase, but this is all very extremely important. And so, yeah, also the stability here, we have 1500 hours. I mean, this is the full solar light on it, and at maximum power point. So the cell is held under maximum power point condition. It delivers power all the time, the maximum power it can deliver. And it's held at 40 degrees in addition to the temperature stress. And so you can see the target is with the thiophene derivative. There's hardly any degradation, say less than 10% or maximum 10% over 1400 hours continuous illumination. And so that's very impressive. And so a simple molecular modulator like this can buy you this big stability increase. And yeah, the other molecules, I won't insist on, they're all similar. Here's a cyclo, different, what this was we go back, this was a paper where we used cyclohexyl, ethyl ammonium iodide. And so you can imagine that the ammonium group inserts into the surface of the perovskite by replacing the A cation. And so it makes some kind of a self-assembled monolayer. And here we see again the recombination. This is photoluminescent decay. Slowed down, this means radiationless recombination is blocked by the mediator. And you get a higher voltage, you get better stability. And this is for another structure here where we use a PIN configuration. So there are many examples for this where with the right chemistry, chemical design, you can really get highly stable systems. For example, this is here in the dark. So, I mean, it's just shelf life over 6,000 hours. But the operational stability is key. I mean, there you hold the cell under full light and you draw maximum power and you increase the temperature at 45 degrees, here even 75 degrees. So that's an amazing result. And yeah, and the efficiency, it decreases only very little. So recently we published 2 papers, one in Nature and one in Science, and these are on the Nature paper is also on a passivator where we use formate to remove defects, but really very recently we have changed the electron selective contact, and we moved to tin oxide nanocrystals as electron selective contact. And that work was published this year in Science. And yeah, so let's take my sweater off. It's getting hot here in my office. And so yeah, this was a very nice discovery with the Korean group, Professor Kim and the 2 Kims, and also our colleague Hagfeld. And it shows that if you use a quantum dot tin oxide layer, you match better. The quantum dot shows a larger band gap than the normal tin oxide nanoparticles. And so the quantum size effect increases the band gap. And so for the tin oxides, mainly conduction band moving up to a higher level, and that matches perfectly the perovskite. And so there we can get better extraction of the carriers and better photovoltaic performance. And yeah, so it's very important to also work on the electron selective contact. And finally, some of the efficiencies we have obtained. And for example, the message here is if we don't, here we use the between the perovskite spirometer, we have a passivator. It's octyl ammonium iodide. If you don't use that passivator, you see the photoluminescence goes down by a factor of 10, and you get much poorer performance. And so to get to those high values, you need to work on the contacts also, not only on the perovskite itself. And so, yeah, these are certified values. And yeah, let me finish my talk and talk to you just for a few more minutes about artificial photosynthesis and fuel generation from sunlight. And so it is clear that, I mean, according to the Shell scenario, I just quote the Shell scenario, the oil consumption will come down, and instead we will have hydrogen as a major energy carrier, or fuels generated from CO2 by sunlight. And so so that's a scenario that becomes very likely. And so how do you make hydrogen from sunlight? That's you can do it in two ways. Either you use a photovoltaic cell and combine it with an electrolyzer. And so that's, for example, is shown here. You have two perovskite cells in series connected to get the higher voltage you need. And they just, you add the voltage of the two, and then you get about, what should I say, 2 volts at the maximum power point, maybe 1.8, and that's enough to drive the electrolysis of water at the photocurrents which you draw from in full sunlight. But there's also a photoelectrochemical approach where you take a semiconductor. I showed you the iron oxide example where you have the solid itself absorbs light and the electrode and produces, for example, hydrogen or oxygen from light. And so that's, both of these approaches are being worked on in our laboratory. And this is one cell that, yeah, I like to mention it because Sir James Barber, the late Sir James Barber, was a good friend of mine, and unfortunately he passed away. He had some, he had a very bad disease, and but in his honor, I like to show this paper where we had, on his suggestion, we had combined our iron oxide films fast in a way, okay, which is useless, but not all. If you make a nanostructure, you can get the carriers out before they recombine and make oxygen from sunlight. And then we need extra voltage that is provided by the perovskite solar cell. So yeah, that was one approach, which is, I mean, we could split water into hydrogen, oxygen, in stoichiometric proportion, but the efficiency was somewhere around 3%. Okay, not very high, but I mean, it was certainly the highest at that time. And but then, I mean, we got a jump when we just we applied the perovskite cells directly as a photovoltaic element, and we used 2 of them, and so that gave us 12%. That's a science paper that was published quite a while ago with Dr. Lu, who is now a professor in China, in Nankai University. And yeah, and but recently we have used a silicon perovskite tandem, which the tandem cells are always better than having just 2 cells the same type side by side. And so here we get close to 19%. And that wasn't with a top efficiency perovskite cell. I think you can get over 20 now easily by using today's technology with this particular combination. And yeah, and finally, our favorite reaction is the generation of ethylene following the proposition of that was kindly made by the chairman of Saudi Aramco at one Gordon conference, which I attended in Hong Kong. And so yeah, so we have we use here silver. It's actually what you use is cuprous oxide nanowires, but the cuprous oxide under operation condition is largely reduced to copper, and actually there's some silver islands on that copper. That's the catalyst we used here. And you see, if you write this reaction down, the conversion of CO2 to ethylene, well, how many electrons do you need for? Well, it's a 12 electron reaction. Okay, so making 1 molecule of ethylene requires 12 electrons and 2 CO2 molecules. It looks like a very complex process, and you wouldn't give it a lot of chances, you know, just from the electrochemical point of view. But copper does it. The copper is actually an invention by Professor Hori from Japan many years ago. He found that copper is the only metal where you can make alkanes from CO2 with significant Faraday efficiency. And so So then what we did was we coupled this to perovskite, triple perovskites cell, and yeah, and we got the whole reaction going, CC coupling, and so the reduction of carbon dioxide to ethylene was coupled to the oxidation of water. It's like the photosynthetic reaction. CO2 is fixed in the form of an organic compound, and water is oxidized. Water is the electron source to reduce CO2. And well, I mean, this still is the efficiency was like between 4 and 5%, but we are now using flow electrodes that have much higher efficiencies. We got, for example, 20% efficiency for CO2 to CO conversion recently. And so this, so there's still a long way to go, but it looks very, very promising to tackle also the direct conversion of carbon dioxide, removing the greenhouse gas from the atmosphere and fixing it as ethylene, which itself becomes a feedstock of like polymers. It will be stored in form of a chemical. And so now comes the end of my lecture. And I show this slide to you because Nicholas Hayek was the former chairman and CEO of the Swatch Group. You probably know the Swatch is a famous Swiss watch. And he, you see on his left arm, he has three watches. It shows you he's a watchmaker, okay. And so, but he was also a visionary, and he wanted to absolutely make a car that would run on hydrogen, and so he in his lifetime he finally convinced Daimler, Mercedes, to make a car. It's called the smart car. I mean, you probably know that car. It's a small car, and my brother is driving one that is electrically powered. And and now we even have the hydrogen power. So his dream became true, that you could make hydrogen. His idea was that every household should have his solar panels and electrolyze water with the sunlight and make hydrogen, or make a fuel, if you like, and drive with their own fuel, their cars. And I think that's actually a likely future scenario. And here we have the fuel cell car now. Toyota is running on hydrogen, and the electric cars, of course, are now a big commercial success. So I finished saying that Bill Gates also became very interested in this topic of solar fuels. And in 2000, I think about 8 years ago, he invited me and Professor Nate Lewis from Caltech to see him he lives close to Seattle, and so we met with him for 4 hours and convinced him. He's a very curious person. He asked me all sorts of questions like, what does quasi-Fermi level mean, splitting mean, and all of this. So yeah, so he has now set up this, discover this fund, and it's a Breakthrough Energy Ventures. I'm sure that there is some investors from Saudi Arabia also involved in this. So quite a few companies have now already benefited from this. I know one company in Israel, they developed new electrolyzers for water splitting. And so with that, I come to the end of my lecture. Here's the beautiful Lake of Geneva. I hope you can visit us in the near future. And our lab is shown with a red arrow there. And the mountains, the Swiss Alps. We are very grateful to our collaborations. We had a long-standing collaboration with KFUPM, still ongoing. We have one student from KFUPM in Massaoud with us, and 2 students have finished their PhD with me. They're back in KFUPM, and they were excellent. They both have been proposed for a prize here for the EPFL, a doctoral study prize. And so we maintain very, very close contacts to Saudi Arabia. And here's the group, today's group. And yeah, here's a group photo, and here's Massaoud on the right side. You can see him. And but you see, this was a kind of a gloomy day, and on the lake, some fog. But when you go to the mountains, you're above the fog. You get the sunshine. And so, yeah, and so this winter I enjoyed skiing. I got my daughter bought me a new skiing suit, okay. And my daughter Lillian bought me that suit. And so it's really enjoyable environment. We are very fortunate to have this environment. So with that, I finished my talk, and thank you for your attention.
Thank you very much, Professor Grätzel. It was obviously a long, experience shared in this 1 hour. But amazingly, the lesson, what we can definitely being a student can take, how understanding the chemistry and manipulating the chemistry of small molecules can lead to big inventions. So we have a couple of questions already in the chat window. I will request first the panelists if you want to have some question from Professor Grätzel. So you can go ahead. Otherwise, then I will read the questions from the chat window. Any panelist, please? So I see maybe no, or maybe Dr. Shahzada. Shahzada, please go ahead.
No, please you proceed with the questions. I will request you to do.
Okay. So we have first question from Professor Wright. I am happy to use one of your paper to prepare solar cells with my students in the lab. My question is about environmental sequence of the fabrication of solar cells.
Yeah, so I mean, we have talked about different technologies here, and the dye-sensitized cells have been gone through the scale up, and I showed you some real big panels and stability and all of this, and today they can be purchased, and they have found 2 types of applications. Now the production itself, it's fairly straightforward. I mean, it's not like you have to go to 1,000 degrees and like in the silicon, or even more than 1,000 degrees, and purify your materials. So you buy the glass panels. They are conductive glass panels, and they use FTO, fluorine doped tin oxide. That's better than ITO. It's much cheaper and much more stable. And so, yeah, these are the collectors, the transparent collectors, and then you print the a screen printing procedure. You put the nanocrystalline film on the glass, and you dip the glass sheet in a dye solution. Within a few minutes, you have the dye on the surface, and then you just have to assemble with a counter electrode and inject the electrolyte through holes. I have a panel like that right next to me here that has been made exactly like that. Now the issues come. If you go to large panels, you have to be very careful that they fit. These stripes have to be adjusted so there are no leaks and no short circuits. So making a small cell is a child can do it. A 10-year-old child can do it, but scaling up requires some experience. And fortunately, there are people now that have that experience.
So thank you very much, Professor Grätzel again. So actually, there are a lot of questions, and I'm really sorry if I will not be able to cover all because of the short time. but we have someone from the audience, Professor Tariq Kandil. So I unmute yourself, Professor Tariq, and you can go ahead.
Assalamu alaikum. Do you hear me, Dr. Tariq?
Yes, yes, we can hear you. Please go ahead.
Yeah, thank you very much, Professor Grätzel, for the very nice and interesting presentation. Actually, I have two short inquiries rather than a questions. So it's very interesting to have this dye-sensitive solar cell with 1.24 voltage. So could you please elaborate a little about the reason behind that, the used redox shuttle in this case?
Yeah, this is a good question. I should have mentioned that in this particular cell, the redox shuttle was a copper complex, not the iodine iodide. When I said this is double as much as not a little bit less, say with the iodine cells, iodide cells that are now commercially used, you get about 700 millivolts voltage, and but 800 maybe if you push it. But this was 1.25, but that's only part is the merit of the dye. As you guessed correctly, the redox electrolyte was also adapted, and we have benefited from the work that was carried out also in other labs with the copper complex, for example. Marina Freitag is now a professor at Newcastle University. She used to work at Uppsala with Professor Hagfeldt, and they came up with these copper complexes. And so the copper complexes are now the forerunners. They give very high voltage and also good stability. So they give also the 15% cells, and this couldn't be pushed further, I'm sure. It's not only our merit, but to answer your question, yes, the redox electrolyte was changed. That explained part of it. Not all not all cells that use copper electrolyte will give you that voltage. So we don't want to take away from the merit of the student, Marko Stojanovic, who made that dye.
Okay. So I hope, Professor Tariq, your question is answered, and I'm really sorry because of the short time. There are like 10, 15 more questions. I will just ask the last question because we are running short of time. And this is one of the audience, Dr. Muhammad. He asking when we will have commercial perovskite solar cells and what is the scope of inorganic lead-free perovskite solar cells?
Yeah, so commercial perovskite, that's a real good point. I'm myself involved in a project to set up a production plant in Turkey with the NTU Singapore, and so pilot plants are already being worked on for a while, and Oxford PV is working on this, and other companies are working on the tandem with silicon. So yeah, it's around the corner, but I mean, we are all saying that it will probably take 3 more years that you can really buy panels that are commercially viable in the sense that they will last for 25 years and have a high efficiency that is commensurate with silicon panels. Don't forget, I mean, silicon panels today are being sold for about I think it's the panel is $0.4 a watt, a peak watt, and the efficiency is 20%. So one, you know, the perovskite still has a way to go in to make sure that the stability is there. It's been improving, and we get amazing results over long times, but it still is a research, and also one has to work on the scale up. The efficiency is the best certified panel module is 17% for perovskite. So still under the commercial, the silicon is at 20. That's a large panel you can buy, okay, and so it's, I mean, it's not surprising. I mean, silicon solar cells have had, I don't know, 70 years to come up and we just have 10 years to come up with the status. And now you're asking for the lead-free. Yes, that's still a research area, and but I would say what the tin chemistry is really promising. The tin version is promising in my opinion. It has a big caveat. The cells are unstable in air. In other words, the tin gets easily oxidized from tin 2 to tin 4. And but I think as chemists we know how to play tricks with these passivator molecules now, and I'm sure that the stability has also been going up of these cells. I'm sure that at the end this can be managed. It just will take a while. This tin, it will take longer. I don't think we will see commercial tin-based systems out in the next 5 years, but maybe I'm wrong. But for lead, they have a chance to be out in the next 5 years. And I mean, there's nothing wrong with the lead if you contain it, if you have a solar field and you contain it with a fence and glass panels. There's nothing wrong. Telluride is entirely sold like that for solar field, and they have cadmium and tellurium in. These are also very toxic materials, but it's selling at gigawatt scale.
Okay, so I sincerely apologize for this that I'm not able to ask all the questions from the audience because of the shortage of time. Trust me, I do have many questions, and I would request Professor Michael that I will send probably an email, particularly on the quantum dots.
Sure, please ask your question by email.
Yeah, thank you very much. And please, we have 25 participants in this hall at the moment. So join me to say once again the thanks. To thank you, Professor Michael Grätzel, for joining us. Of course, he is with us, and we will have at the end of this forum some panelist discussion, and we can repeat, maybe we can ask some questions at that time. So thank you very much, Professor Michael. So our next speaker is Ikerbasque research professor, Dr. Shahzada Ahmad. Professor Shahzada Ahmad has almost like more than 15 years of experience in the research and development in chemistry and material science. After finishing his PhD, he joined Max Planck Institute for Polymer Forschung, rather auf Deutsch, Polymer Research in English, and EPFL Switzerland as a postdoctoral fellow. In between, from 2012 to 2017, he was a program director for a corporate research centers, Ebengoa Research. He has like 7 families of patents, including like 23 different patents with 3 books, 8 book chapters, and more than 150 publications. Currently, he is the editor-in-chief of Emergent Materials and working as an editorial board member for a couple of other journals. Fellow of Young Academy of Europe, Royal Society of Chemistry, and again, many more. So I will not go again, Professor Dr. Shahzada Ahmad, into much details because we are having a rather limited time. So please, we are happy to have you here, and we are looking forward for your talk, engineering the halide perovskites and designing of charge selective layers of efficient light harvesting. So thank you very much, Dr. Shahzada, and it's over to you. You can share your screen and unmute yourself. Thank you.
Thank you. Thank you very much, Dr. Tahir. Can you see my full screen?
Yes, we can see your screen, but if you could go into presentation mode, that will be
I think it's
helpful.
a presentation mode because it's connected to a computer, a desktop. So
okay, so anyhow, we can see but it's not in the presentation. Yes, no, it's in the presentation mode. Thank you.
Okay, thank you. Good afternoon, good evening, in which time zone you are, and thank you very much, Dr. Tahir, for organizing it. And it's glad to see more than close to 150 participants today, and many more on Facebook and YouTube channels. It's a great pleasure for me to speak to you and also collaborating with you. But in the meantime, it's very difficult to speak after Grätzel. But it's not only difficult, but challenging also to keep the audience intact with the world-class science we presented today, because Grätzel has been my mentor and supporter for the last 15 years, and I owe him a lot. So thank you very much to also making the task easy and attending my invitation to give a talk to the Grätzel. Today, as the title, as Nawaz said, I'm going to speak about Halide perovskite. I will skip many things because this has already been done, but I will focus more on charged selective layers, which is the organic component. And so this is outline of my talk will be why we need to do research, emerging PV, new concept in PV. Then I will give you a flavor of my research about how we can make dimension and a stable perovskite. We have to work on methyl ammonium and bromide free perovskite. We will do some example of interface engineering of the 2D material and understanding, deciphering the kinetics behind the devices. Very important, but we do that and we present what the result. So this is not only a research, because solar cells is the poise to, we are educating young people, we are inspiring them, and we are connecting countries and people, because this is very important to tackle the coming energy revolution. And we don't have the capacity, and as Grätzel said, silicon cannot compete. It doesn't matter if it takes 5 years or 10 years, but we need new technology to enter in the market and which can get measured. Today, our society is going an unprecedented time. If you notice that, in the similar month, same month, you will see from August, there was a big fire in America. The glaciers are melting farther than expected. There are floods. In the meantime, there are a drought in different parts of the world, all in a single month. So, and this is making a displace of many housing and people. So energy catastrophe is eating the fabric of our society. And apart from this, for the last 2 years, we are facing another challenges. And of course, for the last 15 days, we have another third challenge is also due to gas and oil. So for the last 2 years, we are facing another challenges. So there was a very good story on Time magazine saying if vaccine is important, renewable is equally important, because we cannot afford to face any new challenges in the future. Emission is a big problem. Maybe energy you can produce, but emission is a big problem. So this is a picture I took from the Time magazine saying, if vaccine is important and we have to restart the economy, we have to rerun the economy, we need renewables. And renewables is very, very important. And how we have progressed? Our society has progressed a lot in the last 5 billion years, from Stone Age to Bronze Age to Iron Age to Middle Age, in 1950 Industrial Age. And now currently we are living in informatic age, information age, where everything is available on a click. But how this is possible? We need new materials. We need new materials for computing. We need new materials for solar cells. We need new materials for battery. And the famous wording is remind me from Ahmed Zaki, the longest serving Saudi Arabian oil minister. So we will not run out of stone because of lack of stone. We will not run out of the oil because we lack of the stone. Similarly, the oil age will not finish due to the lack of oil. The emission is a big problem, and today Grätzel gave a very good example today about hydrogen economy, which now Saudi Arabia is betting more on hydrogen-based economy and want to be a leader in hydrogen. And as Nawaz has updated me, that there are a lot of audience from Saudi and Aramco in this today in this talk. So we need new materials to harvest renewable energy. Doesn't matter it's the solar cells, batteries, or hydrogen production, or CO2 conversion to clean energy. So for this, we need to develop new material. And let me take you back to a voice through a time that where we are today. And as a business means we go that there's the 3 generation of solar cells. H1 is everybody knows it. It's a very good milking cow, silicon solar cells. It's a hugely deployment. Then there are 3-5 solar cells. It was invented, but it's also very costly now. So it's limited to for a special application. Then 80s has come to thin film solar cells like CIGS and castorites. CIGS has the indium. Indium is very costly. So if you replace indium with zinc, you have a castorite solar cell. For the last 35 years, researchers across the globe, of course, Grätzel has been one of the pioneers for the pencil cells. And they have developed an emerging photovoltaic and nanostructure solar cells, in which there's a disensitized solar cells, organic photovoltaics, and perovskite solar cells. So the facade that you have just seen also in previous talk of the EPFL. So these are embryonic technology. We have to take the bet. We have to take the bet and we have to make it work. Just to give you a flavor of why we want to push it, the silicon is 300 micron. And the active thickness in the perovskite solar cell material is 300 nanometers, an order of magnitude lower material, will of course cut down the cost to a large extent. This is not the main point. The other point, Silicon, we need 99.9999959 purity. And this demands annealing at 1400 degrees centigrade. This is not the case with all these emerging photovoltaics. All of them are performing today. All emerging photovoltaics are close to 20%. Perovskite is being the winner, and the calculated cost is very, very low, the LCO here. Why we need them? There's a huge demand, and the current photovoltaic deployment is not sufficient to attain carbon neutrality, which Europe and other countries are committing to achieve by 2050. So we need 100 or 1,000 times more carbon neutral deployment of the PV technology. If we can functionalize them, put them on our facade, on window, with aesthetic benefit, that will be even better. And low amount of material will minimize the cost. The life cycle should be 25 years. This is the major challenges which all these emerging photovoltaics is facing today. But this is the science and chemistry. We hope and we believe that in future we will be able to tackle it. And by the Internet of Things, there are more and more, we are using sensors and devices. So dye-sensitized solar cells or perovskite solar cells, they are also very good for self-powered sensor. You know, all the automobile industry is changing, they're reinventing themselves because all these sensors, they need a battery operated sensor. Because earlier they were meant to gasoline sensors. So there are a lot of huge demand for Internet of Things and making self-powered sensors. The cost should be less than 20 cents watt per peak current from the current 30 cents, and also the current cost is not true. We have to develop an ecosystem. If the solar cells, if the materials are manufactured globally, if their devices are manufactured globally, so this will all create a very good ecosystem and clear jobs. Europe cannot just sell the solar cells and just cannot deploy it. And we need to make a synergy with the current system like greenhouse gases, so that the greenhouse for our plant, for vegetable and food production can be self-sustainable, self-powered. So this type of synergy we have to create it. Coming back to here, if you will see, I have plotted this is an NREF chart we have seen many times in a different talk of the solar cell. So if you see the red color is been like increasing like a rocket, and now we have it almost 25.5% of the Grätzel lab. And organic solar cell is also increasing, 18.2% is satisfied, but 20% has been also reported in the lab. And the amorphous silicon is almost flat, don't see any input. So this is the fantastic research with 10 years back, a decade back, which has been invented. Everybody, the whole community is working out. So we have, for any technology, we have a golden triangle. So we have a low cost, we have a high efficiency, but what we lack is high stability. And this is the people are working on that one. But in the meantime, we have challenges, and these challenges is there are some challenges. There are some challenges in the meantime in the perovskite solar cells. It's a phase transformation. If you take methyl ammonium iodide, MAPBI3, the basic one which everybody started, at 80 degrees change from one phase to another phase. Then we have halide segregation, because we get very excited when we get a high efficiency with the use of mixed perovskite. But then we learn that under the light, the halide, I will show you how, halide gets segregated and they form a cluster of bromide and iodide together. Under light, some of them also show ion migration, crystal size expansion, and high band gap and low band gap. So if you look at this crystal device structure, so this is our device structure of mesoscopic perovskite solar cells, which of course originated from a dye-sensitized solar cells. And if you look at the mesoporous titanium dioxide, is almost 100 nanometer. Perovskite is the active layer is 400 to 500 to 600 nanometer, and then there's 100 nanometer of HTM there, and we finish the device with a 100 nanometer of Ecole. So whole device thickness is less than a micron. Whole device thickness is less than a micron. What my lab is doing is that we are more interested in full value chain. We synthesize new material, new perovskite, new N-type and P-type contact. We characterize them.
I'm sorry, Professor Shahzada, to interrupt, but your voice is not so clear. So could you please maybe check your mic, or you could be near the mic?
I am near the mic. Sorry for that.
It's better now. It's now better.
Okay, now it's better?
Yes, it's much better. Thank you.
Okay, so I increase the volume.
Thank you.
Okay. I increase the volume. So you can see that now, right? Nawaz, can
yes,
you see
it's
this?
better. It's better now, and I can see the presentation, but please go into the presentation mode.
Now you can see that?
Yes, yes, I
Okay.
can see it.
Okay.
Thank you.
Okay. So what my lab is tomorrow, we are full value chain from metal devices. And if we are not successful, we take the help of our friends in simulation and computation feedback to develop new material or giving a renaissance of material. And so what is demanding today to make perovskite vehicles? So compositional engineering, today you have, Grätzel has shown a very good example of FAPBI3, which is a much robust material than the earlier one. Passivation strategy to minimize the defect because perovskite is highly polar. And there's a not very good interface formation between perovskite and the whole selective contact. We need to develop a rational and unreactive charge selective layer, P-type layer, which is dopant free, can be better, and avoid the use of dopant and additives. And the perovskite is not only a good for solar cells, it's a semiconductor. And semiconductor has a range of different applications like light emission, lasing, radiation, X-ray converter, quantum devices, neuromorphic devices, which we also started to work on. So this is a lot of application. If we can understand, if we can develop a stable perovskite, that's a much better on that one. This is the whole range we are working on, making a new type of perovskite, passivation strategy, different type of HTM developing, hydrophobic doping, and interface engineering to make the perovskite stable. When we started to work, just to give you an example, a flavor, it was the crystals were very small, methylammonium tetraide. Now the crystal is larger. Even sometimes we have even more than 1 micron or 2 micron lined crystal. So if we will maximize the crystal size, we will reduce the defect. If we will reduce the defect, we can harvest more energy. And we can get lesser recombination on higher voltage. What we do is solution process and thing, but there's another school of thought. There's some people who are doing evaporation or sublimation of the perovskite structure. So this we can also do that. You can sublimate, evaporate perovskite molecules and the crystal, and then you can see the microstructure. They form a smaller morphology, but you can precisely control the thickness. This is a good thing about this evaporation. This is methylammonium, this is mixed perovskite, cesium formaldinium, and tin. So there's another school of thought. Many other research groups are also doing evaporation of the perovskite materials, in which they can control very nicely the thickness, so the device can be reproducible, and also they avoid the use of clean solvent. Coming back to what I said, the mixed perovskite was very good, but what we found that in the light, you see there is a halide segregation. In the dark phase, they are very good, mixing is there, but in the light, they have halide segregation. The iodine are at one places, the bromide are under one places. So, and then by doing so, they form high band gap domain and low band gap domain. If you will look for the AFM and Kelvin probe force microscope, you will see they form a high band gap domain and band gap. Similarly, there was a very good paper with Joachim Meyer, and there's a demixing of ions. They also studied the same. There's a demixing of ions, and they call a photo demixing because on the light they mix it, and the devices are not good. And if you look at the tolerance factor here, so tolerance factor is close to 1, which means this perovskite is more stable. And formaldinium is the case now, which was not the case with methylammonium and other types of perovskite. And similarly, we have been also working like that also FAPBI3. We have been working for FAPI powder, and this is self-processed powder, so you can just dissolve in any ink, so it will be semiconductor ink. And what we noted that if you will incorporate cesium, the annealing temperature goes drastically down from 150 to 80 degrees because FAPI demand annealing at 80 degrees. Sorry, 150. So if it can be annealed at 80 degrees, so it means we can also think about the flexible surface deposition of the FAPI. And this is the crystal also in 80 degree. You can see it's very pretty, not very large size, but regular size of a crystal. So by doing powder methodology, I think we can all the unreacted lead can be dissolved here, and solar cell performance and especially the reliability will be better. Recently, we have been doing from this was the alpha papis, from alpha papi, so delta papis to become to alpha papi means we can make the black powder ourselves. So if you look at the conventional formaldinium lead, after some time it became yellow color, 100 hours. Delta papi, which is you mix, you deposit them and heat them, it became yellow. Also try to become yellow. But if you will make alpha papi, it remains black even at 100 hours and 1000 hours of light exposure. Similarly, if you do thermal exposure, is the black color. There is no change in the absorption, but it is more stable. And then we calculated the micro stain here, and this micro stain is less. The crystals are more robust. They are like shockers. They can absorb more shock. And then we saw that Auerbach energy is also following the similar trend. So Auerbach energy decreases. If Auerbach energy decreases, our voltage deficit will decrease. So in a higher voltage, we can obtain it. So Auerbach energetic ordering. So this all suggests that the powder methodology and this one is the energetic ordering is increasing, and we can have it more hydrophobic, and the crystal ordering is close to perfect here. This is a hexyl methylamidazole pentafluoride phosphate. This paper will soon be out here. This is the Harris made a video of FAPE. This is the new research we have discussed with Professor Grätzel. This is a new FAPE we have been working on last 6 months here. And you will dissolve in the water. It doesn't change your face. So it remains black. But now we are in the process of optimizing the performance. The initial performance are not very attractive, but now we are in the process of optimizing the performance. You can see it became yellow colored, so it will not work. While our additive engineering base is still black, so you can expect that the device is working as more robust. So we are in the process of additive engineering, optimizing the performance and its solar cell material. We have recorded the PL also. Hopefully, we will be another 2 months. We will update you with the better results. Now coming back to the famous word, the interface is the device, is the heart of the devices. And this we did it, we used 2D material, not 2D perovskite, 2D, this transition metal chalcogenoid materials as an interfacial layer, as a very thin layer. And we put them in a polytriaryl amine, dopant free, because we want to increase the stability of the solar cells, not only performance. We cannot compare to Grätzel of 25%. So by doing this, we also thought that the energy level became more aligned and the voltage is significantly increased.
Sorry, Professor Shahzada, again, your voice is sinking. So kindly.
There is, I think, echo in my office. That's why.
I think that's better now.
Okay.
That's better now. Thank you.
Yeah. Okay. So this is the voltage increases. The voltage significantly increases. And this also increases the performance of the devices. And the performance of the devices, we have a 19% close to it. And this is one of the best because it's dopant free. There's no dopant used in PTA and all that. But the significant part was the device stability increases to a very larger extent because 2D material are more robust and hysteresis also decreases significantly. But why this happened? We did a range of electrical characterization with physics, now indirects, and we found the activation energy is lower, so the charges can be more fun. Attempt to escape frequencies also became lower. Built-in potential was high. Built-in potential was higher. That's why we achieve higher potential, higher views. So this is the helping, and now if we learn from that MOS2 was working, we repeated the story with different type of, we are in the process of studying different 2D materials. So tungsten sulfide, this was a cover of JMC, I think last year. So we use tungsten sulfide here also due to the band alignment and also the voltage increases and the devices perform very well, close to 90% and 20%. If you see the recombination, if you look at this electrical merits here, the hysteresis decreases, the charge transfer resistance increases, and recombination resistance decreases. So all these are the favorable things for the devices. And our aim was more to increase the stability, which you can see here, maximum power point tracking for 1,000 hours, 2,000 hours. It should improve performance than the control device without any 2D materials. So the 2D materials are very good, and it not only increases the stability, but also align the energetic levels. And by doing energetic level, we can increase the voltage significantly. And also we found that the device became, the photocurrent became more saturated at very low voltage if you will place it 300 millivolt if you place in 2D level. This is, I think, we are collaborating with King Fahd University with you of carbon nitride, because we learned from the 2D material are very working well. We can as an interlayer we are using them. So why cannot functionalize 2D material? So like NH2, it will have a double effect. They will do passivation also, and then with this 2D material will increase the stability. So we got two different type of 2D materials from you. It's a carbon nitride, solvothermal, and solid state synthesis, and we made the devices out of it, and the devices give higher performance. Naveen has new results with close to 20%, and the stability is also his study, which he reported to has increased. Not only this, we studied with solid state NMR and other techniques, and we found as they are also very good in coordinating this amine group, NH2 group, is coordinating with the uncoordinated lead, and this is why the higher stability can be achieved. We are more interested also not only the electrical merits to know the device kinetics, but ultrafast spectroscopy, Kelvin force microscopy, to know different type of mechanism, different charge transfer rate, what is going on, because all this knowledge allows us to develop new materials. Like here, if we do that, because the 120 femtosecond ultrafast spectroscopy, with the Kelvin probe, we learned that there was a blockage at the hole blocking layer because the spiro is not able to efficiently stack all the holes. So there was a traffic jam here at the interface between perovskite and HTM. So these all allows us to develop new material, and we develop new material, different type of organic semiconductors. I think Samana is doing a very good job. And this is an organic semiconductor. It's not only good for perovskite, but it's the range of other applications. So many groups are working on organic solar cells, light emitting diode, field effect transistors, and optical sensors. But we are using as a p-type layer in our solar cells. You can see they have different colors because they absorb in a different energy level. But for perovskite, if you want to use them in a perovskite, we have some requirement, because the first and the foremost is you should be soluble in orthogonal solvent, and the energy level should be aligned with the perovskite, with slightly bending there. And hole mobility, it should be for 10 to the power minus 3 Siemens volt per second or close. This is with the spiral. If it can be achieved without doping, then it's an accident, because doping is a trade-off between performance and stability. It should be optical transparent for those people who work on a PIN structure or tandem devices. So it should be optically transparent so that it doesn't absorb more light. Thermal and morphological stability. No glass transition temperature less than 100 centigrade. It should be the cost effective. Generally, we buy a spiral. Spiral is a very costly material. So there are different types of inorganic material have been reported: copper oxide, copper iodide, nickel oxide. Similarly, a spiral, thalocyanine, polymeric is PTA and P3ST. So different type of, this is a very highly cited review article with Grätzel. We wrote it in 2016. So it is one of the, if you are more interested in knowing about whole transport material for perovskite, I think you should, I will recommend this review article to. And then there are, if you look at this different family of whole transport material, spiral bifluorine, which is spiral commercial product, which is the most efficient and workhorse, is 25% has been reported. Then we also found a new family of triazotroxine, close to 20% is being reported. Halfine, which is a very well-known family for organic solar cells and semiconductors. Carbazole, triphenylamine, thalocyanine. So different families. These are the most reported families. HTM in organic solar cell has been reported, and more of this, all of them are giving very good performance. But the spiral bifluorine, which is commercially a spiral, is the most efficient one. But we have to develop new cost-effective, which can be developed with a simple synthetic steps, and it should have a high hole mobility, stability, and efficient hole extraction. For this, we need aligning energetic level so that the voltage can be. Just to give you a recent example of this pyridine carbazole one. So we changed the position of pyridine as a core and carbazole as an arm. We took a different position 5, 6, 2, 5, 6 here. Just with pyridine, the films were not uniform. Just with pyridine with HTM, the films were not uniform. If we put a carbazole, we were able to form a uniform film, which is very good to interface and charge extraction. And we have a performance equal to spirals, and even higher than equal to a spiral gives 17 here. All this 2-6 position give you higher. But significant part was the cost. The spiral is almost €400 per gram, and this we can synthesize at €30 per gram. Significant part was the cost. The cost is very reduced because it's a very simple synthesis. And also we believe that this pyridinium core will also interact with the uncoordinated lead and will increase the stability. So to look at the devices, 2.6 give less hysteresis, 3.5 give higher hysteresis, and even lower than the spiral hysteresis is almost negligible. It's just a cross section. You will see here this we almost 100 nanometer of HTM we have less. Then there's another family. We put the phenothiazine core here. It's electron donating electron withdrawing. Both group we have put sulfur and sulfonane, and this core we have been working on last year. It's also very easy to synthesize here. The yield was also very high here, close to 80%, and similar efficiency, almost the spiral give 19%, and this phenothiazine with carbazole give you close to 18 or 17.7%. But these are more stable. If you will look, if I have time, maybe if I will show you the stability graph, they are more stable than that one. And then a spiral one, and they are more. Similarly, recently we also published with the position of the group, because this is very important, to position of the isomer, and 2 position, 3 position, and 4 position. And finally, this is the influence. So molecular engineering allows us to find an optimum material, because this influences the microstructure. So these microstructures are not good. The uniform microstructures are good to form interfaces, and also we saw that the electro-optical properties like HUMO level, absorption, conductivity, mobility, all significantly increases. It's the same molecule. If we just change the position of the isomer, 2 pyridine, 3 pyridine, and 4 pyridine, the mobility, conductivity, and all the electro-optical properties changes to a larger extent. So this allows us to do that. Similarly, there was a very good paper last year published in 2020 in Science magazine with fluorinated spiro, and they changed the ortho position and meta position. In the meantime, we were also working on similarly molecule. We were not able to reach that performance in our lab of 24%. Fluorinated molecule, because fluorine is Teflon, and Teflon increases the stability. We all have this understanding of that. And so similarly, we have been also using spiro molecule. This is without fluorine. We put fluorine on a spirofluorine here, and we achieve a performance equal to a spiro here. But the devices, as you can expect, was very high stable. If without fluoro, this molecule is highly crystalline and was not able to form even a uniform film. With fluorine, it was a uniform film. But the good part was that the stability increases to a larger extent. If you will look for this, if you compare with the spiro and without the spiro, and this is the electro-optical quenching of the thing. So it tells us if there is extended charge efficiency. Similarly, I think Meenakshi have been working on phthalocyanine, because we know phthalocyanine give you are not very conducting, but they are very stable one, and they have very good, very sharp color also. So with the dimer of phthalocyanine, we have been optimizing at doped and undoped stage, and 18.32 we have reached. Undoped is 14.2. The ideal will be undoped stage, so the device performance can be remain stable, but sometimes it's not the case to make high performance. So this is, I think, very good performance from the phthalocyanine, because phthalocyanine are not conducting, and we have a low fill factor. So you can also see the fill factor is less than 60, which is not the case with the spiro. You can achieve 75% fill factor. So this is just example I showed you about phthalocyanine, and this is another example that use nickel oxide. And with nickel oxide, we have a very thin layer of triisoprene, which you can say as a passivation, or a very thin bilayer of triisoprene. We take 20 nanometer of triisoprene and 30 nanometer of nickel oxide. So this is the nickel oxide. It was not, so you can see it was a pinholes. So we deposit some triisoprene here. So we thought that this interface will be better. And similarly, not only this, we thought the perovskite crystallization was better, because this is normal perovskite, and on a triisoprene, they show a larger crystals. So the crystallization process becomes slower, and the perovskite yielded a bigger size of crystals here. And this is the device statistics, and so we also achieve close to 20% efficiency here with higher stability in this case here. Now, the last part I want to introduce you is most of this, like a spiro, they need doping. And this doping is a 3 component. Like cobalt oxide, you need to oxidize them. And to increase the mobility, you need a lithium salt, and TBP is the additive to increase the voltage. But this is a trade-off with the stability. And that's why our aim, and most of the people developing a doping for EHT, we can work. But in the meantime, which I have shown an example, but in the meantime, we can, what happens if we will develop a hydrophobic dopant? So in the last 20 years, we have been working on ionic liquid. So we took a TFSI ionic liquid, and we optimized the doping concentration. And we found that it's worked effectively. We also monitored through EPR, and with the charge carrier generation was higher than the spiro TFSI. And this is the cross section of the device, which is, just to tell you, thickness is close to 100 nanometers. So this is ionic liquid if you can optimize, because we know that ionic liquid are hydrophobic, extremely hydrophobic. And we just took the same TFSI which we took for lithium, but we changed the cation here. With pyridinium, you can also take imidazolium cation. And the stability, we optimize the concentration by so we saw the current and the conductivity at 7.8 molar concentration without to give you good performance higher than a spiro. Recently, we have been doing machine learning to optimize our results efforts. If you can, so that it can tell us a path. If the path we can know that, then it will take less time to go to reproduce to make only few experiments. We make 400 devices per week. So we can put all this, we have a huge data set, and we can all this put in system. And you can put a random forest model or different model. You can apply them as k-nearest neighbor, distant breed, gradient boundary, random forest. So these all will minimize our tasks, which that is most of the people that course. And why it happens, you can see the full circle and the black circle. They are very close to each other. It's experimental and computed one with the machine learning. So in machine learning, what happens is 20% they take from experimental, 80% they compute themselves. So it's more closer than the old computational studies. This I can skip the time because this is the castrite solar cells. Okay. Let's go.
Sorry, that's again the sound problem, and please, you have now 3-4 minutes because we.
Yeah, so I'm just on the finishing of what we say. That's the Perovskite. Perovskite is ready to take off. By molecular engineering, we develop different type of organic semiconductor, and these are good candidates to use as a p-type layer in Perovskite solar cell. The fluorinated arm with the triphenylamine core based is emerging as an efficient dopant-free HTM. We have shown example here. By linking topology of core and arm, pyridinium and carbazole, its impact of film affinity. So it's very important to optimize and place the position of the isomer there. What we do is we work in electronic level to optical level to system engineering and process and then device level. So from material to device, we work on understanding. And all these are material are functional material which ensure the United Nations Sustainable Development Goal. And like every technology, is not like no new technology is going to the market. The problem is that the silicon solar cell price is decreasing every year. So this is a barrier to the market of, and we have to also increase lifetime, and we need to support. I think this is the cover page of this fluorinated dopant-free HTM, and this is a book we just published last year with Grätzel. And with this, I think I like to thank all my funding agency, European Research Council, Spanish Ministry, Basque Ministry. And I just leave you this message that future is electric. The future is electric, and emission anywhere is a threat to humanity everywhere. We just cannot close our eyes that the emission is in the undeveloped countries, but it will sooner or later it will also harm us. And with this, I think I like to stop here. My apologies for the sound because I'm also sick today. And so with this, I like to stop here, and I look forward to receiving your questions.
Okay, thank you very much, Professor Shahzada Ahmad. So, of course, future is electric, and we are thankful to you for this electric talk. And mashallah, such energetic, and I special thanks to you because you helped in organizing this forum. Plus, in spite that you had a fever and sore throat yesterday, and you are still here. So, thank you very much. We have only chance for 1 or 2 quick questions, and if there is some question from the panelists, please go ahead. If not, then there is one question from the audience. And the question is, what is the special role of using MOS2 as a layered metal chalcogenide?
Yeah, this is the process of interface engineering, because as we know, the perovskite is highly polar, and they don't form a very good interface with the HTM. So most of the people are also using passivation strategy to overcome some challenges. And here, what we found is that we are not only doing passive, we are aligning the energy band level, band energy. And this you have seen that we have increased, significant increase in voltage by almost 150. And the main thing was that to increase the stability, because they are more robust, mechanically more stable. So they will passivate, they will be a blanket layer for the perovskite. They will protect the perovskite underlying layer. Okay. The 2D material like graphene, everybody knows that there have been oversold story, and it's more robust, more mechanically stable.
Okay. Thank you very much for detailed answer. I think I will just take one more question from the audience, and I cannot see the name, but Zoomer is the name for joining. So could you please unmute yourself to ask the question? Otherwise, Professor Tariq, you can unmute yourself, please.
Assalamu alaikum.
Walaikum assalam.
Thank you very much, Professor Shahzada, for the nice presentation. Actually, I have one question regarding the whole transport layer, because in most of cases I saw a whole transport layer and the metal contact. And usually to have the metal contact, we need a thermal evaporator. So is there a way to replace this whole transport layer and the metal contact by a single layer? Easy to process?
Yeah, well, thank you. But this is the, this whole transport layer are very thin, I think 100 nanometers. And you need a contact to take out the charges. So you can put copper, you can put silver, because both of them, copper and silver, oxidize very fast. So we use gold as a metal contact.
Thermal evaporation is a must, or it can be just by a processing like screen printing or?
But a screen printing, you can do that, but it's another matter of optimization because the solvent will be compromised with the HTM layer. So yeah, this will be a difficult task to optimize, but it's not impossible. You need to optimize it.
Yeah, thank you.
Yeah, yeah. Without metal contact, I think there is a one. I think Michael also pioneered this research of using a carbon electrode. So you can deposit a very thin layer of a carbon paste, and then you can connect with them.
Okay.
Okay. So thank you very much, Professor Shahzada Ahmad. There is another question, but I think from Dr. Mujib Khan, and I think you already answered about carbon-based material. I will forward you this question. Probably you can also write answer, please, to him. So with this, thank you very much. And we will move to our next speaker, Professor Riccardo Ruffo. Thank you very much, Professor, for joining us for this forum. Professor Riccardo is a professor at the Chemistry and Materials Department of University of Milano, Bicocca, Italy. So Professor Ruffo joined as an assistant professor in 2007, and then he was a guest professor at Stanford University like 2 times, once in 2008 and then 2013 on his sabbatical leaves. Professor Ruffo has almost more than 150 publications with more than 100 scientific contributions at national and different international platforms. So the main area of research is in the energy storage and conversion devices. So there are a lot of details again for more honors, awards, and like I'm running short of time, so Professor Ruffo, please accept my apology. I will just hand over the floor to you, and you have 35 minutes, and go ahead. Thank you very much.
Okay, I think you see my screen now, right?
Yes, very clearly. Please go to presentation mode. Yes, thank you.
Presentation mode, so good. Thank you for the invitation. Thank you for the presentation. It's an honor also to be here with Professor Grätzel, which was not just the inventor of dye synthesizer solar cell, but also is an excellent electrochemist. And he worked also on the battery field, where he produced very excellent papers, for example, in phosphate for cathodes and so on. In any case, it's very exciting to work in the battery field for 2 reasons. The first one, they are powering now cutting-edge devices like they are used in cars. So we see real applications on this kind of systems. And at the same time, we still need to work on basic research to study new materials, new interfaces, and so on, to increase the performances, to make better devices, and so on. So it's really nice to work on that at the moment. And in my presentation, I will give you a motivation about the use of batteries. I will speak a little about tools to study and to understand the performances of electrochemical energy storage devices such as lithium-ion batteries. Then I will focus a little bit on the state of the art of the current technology, which is the lithium-ion batteries. And we all know that in 2019, the 3 inventors of lithium-ion batteries become awarded with a Nobel Prize. Then we will jump a little bit in the future, in the near future, with the possible developments in the next 5 to 10 years, and then have a look a little bit further what is going on and what we think we can do more in the future. So as I told you before, lithium-ion batteries changed our life 2 times. The first time was in the middle of in 1990, where they become where they start powering portable electronics, which is the market right now for lithium-ion batteries. But now in the last 5 years, they are penetrating in the automotive sector. And this is driving, let me take the pointer. Yeah, this penetration of the lithium-ion batteries in the automotive market is driving this huge growth in the amount of energy which is stored right now in lithium-ion batteries. And we expect to increase this number by a factor or by an order of magnitude in less than 10 years. This is a strategic sector so important, and then the capacity to fabricate lithium-ion batteries, it's one of the most important technological challenges on a global scale. And Europe and US want to become a player, one of the players of such market, building their own companies and their factories for the lithium-ion batteries. In Europe, the most important example is Northvolt, which is co-located in the north of Sweden. They want to produce next generation batteries in a greener way, in a more sustainable way, see, with a close look to the sustainability issues. At the same time, the cost of lithium-ion battery is decreasing year by year. And 10 years ago, 15 years ago, was about $1,000 per kilowatt hour. But right now we are around $100. So the price decreases of a factor of 1 order of magnitude as well. And this has been driven by economies of scale. It doesn't make sense right now to build batteries, to fabricate batteries in a small factory. You need to build up a gigafactory in order to produce billions of battery per year. And thanks also to the technological improvement. But we know that right now the price of raw materials are growing up. So this decrease of the price may be affected by the cost of raw materials as well. So tools to understand electrochemical energy storage, very often, okay, one of the key points is the cost, of course, we have already seen that. Then there is the energy density, which is the energy which can be stored in our system. And we get this energy density often by what we call discharge curves, charge and discharge curves, where the potential is a function of the time. And very often we do this kind of measurements in constant current conditions, so we can easily calculate the charge, and we plot the potential as a function of the charge. Now, the energy is the integral of these curves, and very important when you have a rechargeable system are the losses. So in this case, we can have 2 losses. One is due to the fact that you are not able to use all the materials that you spend during the charge, during the discharge, so you have charge loss. And the second point, which is a thermodynamic limit of our system, which is due to the second thermodynamic law, is the energy loss, so the difference in the areas of the 2 charges. Then important parameters is the capacity retention, which means if I fix to 1 the maximum charge that I can get from my battery, in how many cycles my charge is lasting without a significant decreasing of the charge. And an acceptable value for example, for automotive application is 20% of charge lost after 1,000 cycles. So based on the performances in terms of specific energy, specific power, batteries can be classified against them, but against also other devices in terms of Ragone plot, which is a log-log plot where we put the specific energy versus the specific power again. And you can see that lithium-ion batteries are the more performing battery system right now, and we're still increasing that. And this is getting competitive with other technologies. There are technologies which can work much faster, but with much less energy, like capacitors. the combustion engine is still on the right top side of this Ragone plot, and we try to get there. While fuel cells are very good in terms of energy, but they pay a little bit in terms of power. So the lithium-ion batteries, which is now in the market, has several advantages, but the main important one is the use of intercalation chemistry, both at the positive and negative electrodes. And this intercalation chemistry makes the lithium-ion batteries a very reversible device. In this device, during the first, which is made by a layered oxide on the positive electrode and the graphite on the negative electrode. During the first charge, I remove the lithium from the layered oxide and I put the lithium into the graphite. So basically, my really cathodic and anodic materials are the delithiated lithium layered oxide and the lithiated graphite, and when I need energy, I can just to put an external load on the two terminals, and I have the spontaneous flow of energy through my system thanks to the spontaneous delithylation of graphite and delithiation of the delithiated transition metal oxide. So the state of the art, let's start from the electrolyte, which is the heart of the battery, where lithium ions is exchanged between the two electrodes. Lithium-ion batteries cannot work with water because the materials that are producing during the charge are unstable in water. So we need to use a complex combination of solvents like carbonates and lithium salts. This combination of chemicals has a very good stability towards the oxidation here, but they pay a little bit in terms of reduction. So basically, they cannot be operated below 0.8 volt versus lithium, but we know that our batteries are working on more than 4 volt. So the key parameter here is the key aspect here is the formation of what we call solid electrolyte interface, which is a passivation layer formed during the first charge at the negative electrode. And this is not just a passivation layer, it's a layer which, avoid the further contact between the electrolyte and the graphite of the lithium. So which will reduce the electrolyte, but at the same time, it guarantees also the transport of ions. So this is the reason why we call that solid electrolyte interface. And it increases the operative voltage of our batteries. We use usually carbonates, which are flammable and toxic, and also fluorine-based salts, which can decompose in contact with water, giving HF. So there are a lot of improvements that we can try inside electrolyte. So the negative electrode is graphite. The history of development of graphite in lithium-ion batteries is very interesting because it started in the middle of 70s with the early trials to use graphite in contact with the propylene carbonate, which is a common solvent in the electrochemistry of lithium, of metallic lithium. But they failed. This was done in Argonne National Lab in US. They failed and they quit such kind of research. Later, it has been demonstrated that lithium can be reversible intercalated into graphite thanks to the use of polymer. And at the end, we discovered that the reaction is perfectly reversible if you use this ethylene carbonate. So if you look at the difference between ethylene carbonate and propylene carbonate, it's really tricky to understand why this molecule is working, why this one provokes the exfoliation of graphite. And the reason it's again this stable SEI layer formation at the interface. So for a very long time, the electrochemistry of lithium-ion batteries has been considered just a bulk electrochemistry related to the bulk properties of materials in terms of storage of energy. But at the same time, this is a message also for the future. We need also to look at the interface again, like we do in electrochemistry usually, which is considered one of the science of the interface. So by changing the interfacial properties of your materials with electrolyte, you can completely make your technology working, starting where a very failure result. So the intercalation of lithium into the graphite is made with several steps, where the lithium is filling the different layers that you have into the graphite, and we can go up to 370 milliampere hour per gram, which is a remarkable value, with several stages. And you can see that the potential is very close to that of metallic lithium. So graphite is a very good anode materials for the lithium-ion batteries. At the positive electrode, we have different materials that can be used. They can classify in 3 different families. One is the families of the layered oxide. Then we have spinels. And finally, the very famous phosphate materials like the lithium iron phosphate. The advantage of use the layered oxides related to the reversibility, the power density, so we can run our cell at higher currents, and due to that, we can get higher energy density. However, these kind of materials are thermally unstable, and we have made a dramatic failure of our battery, resulting in flames and explosion and so on. And of course, the presence of cobalt, which we want to eliminate the cobalt from our batteries. In the case of spinels, they have better thermal stability, gain good energy density. However, the power density is lower. And the use of manganese in many of these spinels also introduce a sort of chemical instability due to Jahn-Teller effect. Finally, we have lithium iron phosphate, which has very good thermal stability, very good time life, power densities, can be used at very high current. However, the voltage of this material is lower than the other 2 classes of about 500, 600 millivolts. So this affects the energy density. And also another point which is less considered is the tap density, because in the case of oxides, we can store much more materials in the same volume, while in the case of phosphate, the density, the tap density is such that we cannot have very good energy applications for that. So in the evolution of the positive electrodes, we are using now a mixture, a layered oxide, which is a mixture of nickel, manganese, and cobalt, like 1:1:1:1, like in this case. We try to increase the amount of nickel, which has a very good electrochemistry properties, and we can try to reduce the amount of cobalt here. But we pay in this direction because the less cobalt you have in your system, the lower is the reversibility of the reaction. So you pay something in terms of capacity retention, and also the thermal stability is affected. While if you increase the nickel amount, you can get very high discharge capacity, but you have a less reversible system and a less stable, less chemical stable system. So we have always this trade-off between reversibility, time life of the battery, and properties in terms of energy density. So what is going next in the future? For the European community, the development of such devices is very clear. And up to 2025, the improvement will be driven by the implementation of high voltage cathodes and increasing the amount of new materials that we can introduce into the graphite. But if you want to increase further the performances of lithium-ion batteries, you have to change radically the technology and avoid the use of intercalation chemistry and look for something different. So the generation 3B, the next one to be, which is expected to be into the market in 2025, should have higher volumetric energy density, very high stability, and a reduction of cobalt in our cathodes. So the guidelines to reach such goals are the development of silicon anode materials inside the carbon structure, a better control of the modular pack level through the battery management system, a better cell integration inside the car, And finally, the use of nickel-rich NMC, as we have already seen, or high-voltage spinners. The case of silicon, and we have worked a lot when I was in Stanford, we have worked a lot on that together in the lab of Jijeesh, which was a professor also involved with your institute. Silicon is a very curious case because it has the highest capacity that you can have. You can reach one material, but it's really unstable mechanically. So the idea is to combine a little amount of silicon inside the normal anodes. And right now we can put 5 to 7% of silicon in our anodes. And but we want to get something around 15 to 20%. So step by step, we want to increase the amount of silicon inside our carbon anode. From other part, we can develop materials working at much higher voltage, like 4.5, 4.8 volts. And in this case, we can change the transition layer oxide with high voltage spinners containing both manganese and nickel. This is work we have done in collaboration with Korean group several years ago. So let me raise a little bit the issue of sustainability. Where lithiums come from, we have two possibilities for the lithium, basically brines in dry salts, in dry lakes, sorry, or minerals. And looking at the figure that we have worldwide, it looks like we have enough amount of lithium to convert all our cars in electrical cars, and this lithium should last for at least 1 century. This is on a resources level. But which is better, minerals, lithium coming from minerals or brines? So basic on life cycle analysis studies, very good one made in this Swedish Environmental Research Institute. They demonstrate that the lithium from brines, which is typically from the South America, it's much better than the lithium from this ore, this spodumene ore, which is coming mainly from Australia. In terms of cost and in terms also of parameters related to the sustainability of the technology, like the kilogram of carbon dioxide, the equivalent kilogram of carbon dioxide, the toxicity, and so on. So if you look at the reserves, not at the resources, we have that the highest amount of lithium is in South America, and it comes from brine, which is a good news. The production, but still the production of lithium is dominated by Australia. There is China, it's a good player, while Chile and South America are, the numbers are growing a lot. But in any case, the problem that we have right now is not in the resources, is not in the reservoirs, because just in the reservoirs we have lithium for not 1 century, but about 20 years probably. But in any case, the problem is that how fast can we convert all the lithium that we have in the resources into a product which can go to the market, typically lithium hydroxide or lithium carbonate. And these sentences from the benchmark materials, it's really, really important. It takes much longer to build a lithium extraction processing plant. Much longer means about 20 years, compared to a gigafactory for batteries, which requires about 5 years. So at the current rate of growth, which is dominated by this automotive sector increasing, we expect shortfalls in the lithium supply chain. And this is a dim picture about that. This line is the total demand of lithium due to the penetration of lithium-ion batteries in the automotive sector. And these analysts are saying that we will not able to follow the growth of lithium, not because we do not have enough lithium, but because we are not able to extract this lithium in a fast way. So considering that we need about 300 grams of lithium to produce 1 kilowatt-hour of energy, we have three possibilities. One is to produce better lithium-based batteries and to increase the kilowatt-hour that we can get from this amount of lithium, or reduce the amount of lithium that we need to create a kilowatt-hour of energy. Or we need to recycle our battery, getting the lithium out of that. Or we can look beyond the use of lithium and using new chemistries. So the holy grail of lithium battery research in producing better batteries is the use of metallic lithium, which is not included in the current technology, what we call the lithium metal batteries. Lithium metal batteries are currently widely used in primary systems, so no rechargeable system. The reaction is very, very fast. It's the oxidation of lithium to give the lithium ion. Sorry for that, okay, to give the lithium ion. But the problem is the reversibility of that. When you try to plate metallic foil like lithium or other foils like copper and so on with lithium plus to give the lithium, what you have that lithium doesn't grow, at least at the usual current rate, doesn't grow layer by layer, but grow with these dendrites. And these dendrites can be detached from the substrate, can penetrate the electrolyte, can give short circuits, which is a dramatic situation in our cell. So if you look at the curve of stripping of the lithium, consuming of the lithium, and plating of the lithium carefully, sooner or later you will get these current instabilities due to the formation of dendrites and then short circuits due to the contact of the anode material with the cathode material. So, but let's make a couple of calculations about this metallic lithium. So the main issue here is the dynamic formation of this SEI, so the passivation layer, which should cover all my lithium, and it's during the lithium stripping plating is consumed as well. So we call this a dynamic SEI formation, where the Coulomb efficiency cycle by cycle is 90% versus the 99.9% that we have in lithium-ion batteries. So considering that 1 micrometer thick lithium foil has an area capacity of about 0.2 milliampere hour per centimeter square, the area capacity of the cathode is about 10 times. So we want to use right now 50 micrometer thick lithium foil with 4 times the required capacity in order to extend the lifetime from tens to hundreds of cycles based on calculation on the efficiency of the process. But if you think about, if you have a cathode where the lithium is provided during the first charge, you don't need the lithium at all on your at your anode. Is the concept called the anode-less lithium-ion batteries, where the lithium, the anode, metallic lithium anode, it's formed during the first charge with the lithium ion coming from the cathode. For these applications, new electrolytes should be developed because the current carbonates cannot be used for that. New morphologies in terms of anodes should be also designed. One of the examples we are working with are deep eutectic solvents, which show preliminary good results in terms of stripping of lithium and, plating of lithium here and stripping of the corresponding lithium here. However, one of the main subject for the use of metallic to exploit the metallic lithium is the use of solid state approach. The idea is to have a material which is able to block the growth of the dendrite. Unfortunately, dendrites are able to penetrate among the inside the grain boundaries of my solid material. I'm not going you too much details about that because I guess that the next presentation will be all about that. So I give to Jijeesh the stage, and he will present all these results. So he's much more expert than me. We have done something as composites, tried to mix together a ceramic composite grafted with polymeric precursors embedded in a polymeric matrix and so on. They are very complex materials. We can extend a little bit the life of our system, but he will give you much more details about that. So the use of metallic lithium also opens the door for the use of not lithiated cathodes. And in this case, we can look to conversion materials where the intercalation reaction is not the main reaction at electrodes. That means we can increase a lot the capacity of our system. One of the most powerful examples is sulfur. I'm not expert of lithium-ion sulfur, so I'm not going to speak about that. This is a very old idea, first developed in Bell's lab in the middle of 60, I guess, 1960. And this idea was renewed in the beginning of this century because the use of nanomaterials to trap the soluble products that are formed during the lithiation. And right now there is a company in UK, Oxy Energy, which is claiming to commercialize the first lithium sulfur cell, which for several reasons are not intended to be used in automotive industry, but in portable electronics. Another good idea would be the development of the very famous lithium-air system. Again, a very, very good attractive chemistry where you mix together basically two completely different devices, like you have the cathode, which is typically of a fuel cell, and the anode, which is metallic lithium. And you have also to combine together two chemistries which are really different and cannot really couple together. In the around 2010, there have been a lot of investments about the development of this lithium air. However, in 2014, there's been a lot of analysis about the system. First of all, you cannot use air here, but you have to use pure oxygen. Otherwise, your device is not working properly. And then several calculations about possible devices equipped with oxygen cylinders or open to air with a catalyzer and so on, provide a figure of merits which were not really so satisfactory. So most of the players, most of the big players now abandon this kind of research. Why we do not, to overcome the issue, let's go back to the issue of raw materials, why we do not recycle our lithium batteries. Again, this is, of course, it's a very good idea. However, there are preliminary open issues, even starting of that. It's not that easy to collect the devices. It's not that easy to identify the devices because every factory use the proper chemistry. I don't want to reveal this chemistry. And now the European Commission is putting strong regulations about that, which are now absent. We need to identify the state of health of the battery because we have two possibilities here, especially for batteries in cars, which may be very big and expensive and so on. Before recycling, we can think about a second use, for example, in energy storage and so on. Regarding the recycling, we have activities here in our department. I'm not really an expert at that, but there are two strategies. One is to use these raw materials directly in new lithium-ion batteries. The other one is to produce chemicals which can be used indirectly. How much time do I still have?
So please, maybe in next 5 minutes, because we are already 5 minutes over the time.
We cut most of the part, okay?
Yeah.
So beyond lithium, which is the best chemistry? This table, you see abundance, capacity, so performances, abundance, voltage of different elements from lithium, potassium, calcium, sodium, magnesium, and so on. The idea is always which kind of device we want to build. Lithium metal batteries or metal batteries, or we want to exploit the intercalation chemistry. Because in the case of the intercalation chemistry, the performances are quite low, limited by this kind of reaction. While for metal batteries, we have problems of reversibility, We need to find out good cathodes, and even the metal production can be an issue. So in the case of sodium-ion batteries, we have developed several materials for that. They have advantages like we can use cobalt-free materials. They are cheaper. The materials used in sodium-ion batteries are cheaper than the materials that we use in lithium-ion batteries. However, the performances are not enough. We have developed these mixine-based materials specifically for sodium-ion batteries, reaching reversibility, which is higher compared to the lithium-ion batteries. But at the end, if you calculate, if you pay attention to the lowest energy amount, you end up with a device which is more expensive than the lithium-ion batteries. However, these lithium-ion batteries right now is a technology which is ready for the market. But at the moment, the large availability of lithium-ion batteries make this transition basically not necessary right now. Potassium-ion batteries, it's very similar to sodium-ion batteries. It can be very reversible as well, but it has the same problem. There are very interesting systems like aluminum and calcium. Calcium is still to be completely explored. Like aluminum is one of the most interesting for two reasons. First one, because several ions containing aluminum can be intercalated in the same electrodes like graphite. And because also it's very easy to produce aluminum foils in our technology. So to conclude, and to stay also on the time, lithium-ion batteries will dominate the automotive market probably for tens of years, unless we start using fuel cell-based cars. The future of lithium-ion batteries is in the use of carbon silicon composite and cobalt-free electrodes. The lithium sulfur battery is a very promising alternative for several applications. Right now, lithium-ion batteries are too expensive to be used on large-scale energy grids. So for energy storage application, we need to find very cheap and faster alternatives to that. In rocking chair configuration, so with the lithium-ion approach, sodium and potassium batteries are good alternative to the lithium ones. However, they are not enough economical benefit to change this technology right now. And the final point is the future battery system, if will be used a metal anode, should look for inexpensive chemistry, considering also the metal production. Because if we have to produce the lithium foils to be used in the battery, well, this is a kind of technological aspect that we are still to consider. Finally, I want to thanks for your attention, all my students that have been working with me in the last years, and of course the funding agencies. Yeah, thank you.
Thank you very much, Professor Ruffo, for like a very kind of from the basics to fundamentals to accomplish the technology. Thank you very much for this informative talk. First of all, if there are some questions from the panelists. If not, then actually there are a couple of questions from the students, from the audience.
Okay.
I will just take probably one or two questions because we are running short of time. So the first question was like, what is the reason of using these polyolefins? And will the molecular weight of polyolefins will have some impact on, you know, on the system?
Well, the next speaker is much more expert than me, so he can answer to this question. His presentation is focused on polymeric electrolyte.
Yeah.
So yeah, I leave this open question to him.
Okay, so it's fair enough. Yeah, of course. I mean, we will leave this question to him. The second question from my own interest, like obviously, I mean, we have different cations, like you also showed nicely, like, you know, aluminium, magnesium, and calcium is next to be explored. But like lithium, in integration and deintegration, will this fit like aluminum or calcium size-wise or something? Like we will have no materials very much, compatible with lithium.
The idea is to have different solutions for different applications. So we
I
will
see.
not have one kind of batteries which will power everything.
Okay.
Probably in the automotive market, the lithium-ion system will dominate for years right now. If the automotive producers want to go in this direction, they are investing a lot of money and they will not change the production for tens of years, of course. But this is also suitable for that. In other applications, like for example, in energy storage, where we do not need a very high energy, we need a very high power. We need that the technology will cost less than possible, at least considering also the round trip efficiency, the cost of the technology should be comparable with the cost to produce the energy. Otherwise, it's an increase of the price, and we don't need this right now. So we need to find new solutions, like, for example, coming back to water-based electrolyte, and to increase the stability of water, to have systems able to work above 2.0 volts in water and so on. So I don't know really how is the future. I mean, it will be difficult to think about that, but for sure there are a couple of technologies like the sodium-ion batteries, which is pretty ready for the market. And indeed, the biggest lithium-ion producers, which is Chinese company, last year they announced the first production line for sodium-ion batteries.
Okay. Okay, so thank you very much, Professor Ruffo, once more. And we will move to our next speaker. But please stay and join us in the panelist discussion session, inshallah. We will have some time at the end. So our next speaker in energy storage devices session is Dr. Jijeesh Nair. So Dr. Jijeesh Nair received his PhD in 2010 from the Materials Science and Technology Department, Politecnico di Torino, Italian University, Italiano, or Italy. And then he was there as a postdoctoral fellow till 2017. Since 2017, he is working as a research associate at the Helmholtz Institute in Münster, Germany, which is a division of the Forschungszentrum Jülich GmbH. Dr. Nair has more than 80 scientific publications, 5 book chapters, a couple of young research awards are also under his name. The main research area for Dr. Nair is cross-linked solid polymer electrolytes for lithium-ion batteries. So Dr. Nair, so it's a pleasure to have you here. Thank you very much for joining. And of course, now floor is yours and you have 30 minutes. Thank you.
Thank you, Tahir. Thank you very much. Can you hear me properly?
Yes, of course. Very clear, very loud. So please.
The screen is okay. Can you see the PPT?
Yes, screen is also fine. Thank you.
Okay. If there is any problem, you can let me know during the talk. Okay. Yeah. So thank you very much, Tahir. Thank you for the invitation and thank you for the detailed introduction. And also it is an honor for me to share the panel with other world famous and well-known and experienced researchers and scientists. So to be frank, Professor Ruffo made my job much easier. So I'm not going to the details about how lithium battery works, etc. But I would like to give you some fundamental or the basic insights about what kind of polymers or polymetrics you can use as polymer electrolytes, especially focusing on lithium metal batteries or lithium metal polymer batteries. So we have already seen different components, what are the importance of anode, cathode, electrolyte, etc. And as Professor Russo has already demonstrated, we can, lithium battery is a success since the 90s, and we are using it in our day-to-day life. And today, the lithium batteries are even very close to our body. So the safety is also a big concern as well. And one of the key words, some of the keywords that is very famous and very widely used are whatever the materials we produce should be eco-friendly, easily available, upscalable, low cost, and most importantly, safe. Why safety is an issue? Because once you look at the batteries, it has liquid electrolyte, as Professor Ruffo already mentioned, as organic carbonates, additives, salt, etc. And this is the anode and cathode is separated by a thin layer, which is a polyolefin, which is a trade name CellGuard, which is a multi-layer system, but it is a maximum thickness of 20 micrometer, even less thicker. But it has either bilayer or tri-layer polyolefin systems. What is the issue with this one? This one, because as they are thin, they can create, when the dendrites are formed, they can be easily pierced. Then the fire hazards can happen, which can, due to the use of organic carbonates, it can also produce gas, for example, carbon dioxide or other kind of gases by side reactions, etc. Additionally, use of liquid electrolyte will lead to a lot of leaking or other kind of packaging related issues. So that will reduce the overall energy density of the battery. And if you want to know something about lithium batteries or lithium polymer batteries, when you are searching in Google, you will see that, oh, lithium polymer, then the suggestions even from the Google is the first one is fire. And the another one, if when you want to check some videos about YouTube, if you search, for example, the first will be lithium polymer battery explosion. So even though we use polymer in the electrolyte or as a separator, the bad name came from the use of this small thin layer and use of organic carbonate. So it should be changed. And one of the ways that we can use, as also Professor Ruffo mentioned, we can increase the energy density by replacing the anode, which is based on graphite, to lithium metal. This is not a new thing that we are going to talk about, but it has been used, lithium metal batteries have been used as a primary battery. Then there was an attempt even in the 1970s to increase, make these primary batteries into secondary batteries. But they have used thicker lithium metal foil and also a separator, but along with the liquid electrolyte. Then what happened is that the dendrites were formed, it was very unsafe, and slowly the research decided that lithium metal is a failure. And then they moved to lithium-ion batteries of today, and which was established by Sony in the 1990s. And that has been very successful since then. Even though a lot of research has been made, the biggest achievements were technological or engineering advancements, whether which kind of materials are used or what kind of packaging ideas or the type of packaging, etc. But now the third revolution could be the lithium metal battery, in which we can use very small amount of lithium foil, or even, as we mentioned, anode free or lithium metal free batteries. So when we use lithium metal free batteries or lithium metal based batteries, we have to resist dendrite formation. And one of the best way is moving towards solid state electrolyte. And this will surely increase the safety. This can reduce the size of the battery, so energy density can be improved. We can produce thinner, and as no liquid is there, it is completely free from leakage of the electrolyte. So this new revolution that is based on solid state system could be could be the chance for lithium to rebirth into a lithium metal polymer batteries or solid state lithium metal batteries. So what are the options we have for solid state batteries? We have either we can use solid polymer electrolyte, which is based on classical PEO or LiTFSI system or other kind of polymers. And on the other side, on the inorganic side, we have inorganic ceramic electrolyte, either based on oxide, sulfide, phosphate, etc. So if you look at the polymeric side, it can be thermally stable, safe, flexibility, because that is one of the advantage. We can produce thin batteries, and physically and chemically, as polymers are comparatively much stable, their melting point or their thermal stability is higher, and no solvents are used, they can be leakage free. But they have big issues like low ionic conductivity at room temperature. The lithium ion mobility inside is slow, that it has slow ion diffusion and kinetics, non-conformer interface with the electrode, because if we use the standard conventional processing of lithium cell. On the other side, for oxide sulfides, again, they are also thermally stable. They are safe. They have good physical and chemical stability. As no solvents are used, leakage free, etc. But their issues are grain boundary resistance, and you need a very high energy for the lithium to mobilize within the crystal structures. And most importantly, when they are produced, they are it is very difficult to produce thin configurations. And you may use the thicker one. So the advantage you may get from a solid state system may not be available for this kind of system. Besides, as again, reference to Professor Ruffo talk, where lithium, we need to use a lot of lithium. For example, in a simple liquid electrolyte system, you may see that one mole of lithium is used per liter. However, if you move to the solid state system, maybe for example, LLTO, 81 moles per lithium is used. This increases the amount of lithium that is used per battery or per cell, for example. So this is also a good challenge. And one of the compromise that we may make is the use of hybrid electrolyte, where we can use both polymer as well as a ceramic electrolyte. So that could be one of the futuristic methods where we can blend all the properties together. And coming to polymer electrolyte, so the solid state conduction is not a new thing. It has been there since the 1830s, where ionic conduction in solid electrolytes were introduced by Faraday. Later, if you look back solid state systems for energy storage itself, even the Daniel cell that you study in the school text or Leclanche cell, even during that time when they produced these kind of cells, they wanted to make it mobile, mobility, because they want to transport from A to B. They want to make it smaller and leakage free, because they were using liquid electrolyte even that time. So since that time, there was an attempt, but however, from the from 1973, when Professor P.V. Wright and his co-workers introduced that lithium-ion or other alkali metal ions can be mobilized within the polymer structure, it was a new opening for solid-state electrolyte. Further, Professor Ahmad and his co-workers have contributed immensely for the development of battery, which today, after several things, even there's a car which is from Bolloré Blue Solutions, which produces solid-state batteries and batteries that run on polymer electrolytes. So these are the examples where we are from 1973 to 2006, where we have a real product. So from the polymer electrolyte point of view, what are the requirements we have? What are the requirements of a material, for example? Whatever the properties that we have from liquid electrolyte, we want that. For example, wettability, eco-friendliness, electrochemical stability, current collector stability, high ionic conductivity, water, low cost, etc. In addition, you also need mechanical strength, dimensional stability, and higher transference number because the conductivity into solid state system is comparatively lower. And the higher transference number can also reduce the polarization at the interface. And besides, the mechanical strength is one of the important parameters, because we are going to deal with the lithium metal, as also Professor Ruffo showed. This can create, if we are using liquid electrolyte in place of polymer, this can create dendrites. And one of the reasons that we have to impart mechanical strength to a polymer membrane or other kind of solid state electrolyte, because we want to avoid dendritic growth and related short circuits. As you can see in this image, you can clearly see how lithium, high surface area lithium is deposited on the metallic surface. So this should be completely avoided, and this should be resisted for a safer battery. So what are the physical properties we require for a polymer electrolyte in this respect? For example, if you know polymers in general, those are semi-crystalline material. It has a crystalline phase and it has an amorphous phase. And crystalline phase cannot conduct or conduct very less the positive charge or lithium to its surface. It's metric. However, the amorphous system, because of its segmental mobility or lower glass transition temperature, it can help the ionic mobility. And if you look at complete polymer electrolyte scenario, you will see that most of the modifications in the polymer systems have been contributed by modifying the crystallinity of the polymer system. For example, here you can see that by adding plasticizers, nanofillers, or blending the polymer, grafting the polymer, or cross-linking, or making different kind of block of polymers, you can achieve different morphology and you can control the crystallinity of the polymer system. Thus, you can improve the ionic conductivity. And this led to several kind of systems like solid polymer electrolytes. You can see even though this is not the ultimate classification, you can see that you have solid polymer electrolyte where no solvents are used, gel polymer electrolyte, which is mostly coming up industrially, even for EVs or other kind of mobile phone application, in which small amount of solvent is used. Other polymer composite, in which you can combine several things, and etc., etc. And if you look at all this portfolio of polymer electrolytes, you'll see that these modifications are made to improve the mechanical properties and ion transport properties of polymer electrolytes. And now let's see how ions are mobilized in a polymer electrolyte. For example, in a polymer electrolyte, especially in the amorphous phase, the chains, the lithium ions can mobilize either within the polymer chain or from one polymer chain to another polymer chain. So this is called intra-chain or inter-chain hopping, especially because, as I mentioned, polymer is a semi-crystalline material. It has amorphous nature and crystalline nature. And the crystalline part of polymer, especially in PEO, conducts differently, as you can see here, conducts differently than the amorphous phase, in which the segmental motion plays a big role. So the glass transition temperature of polymer will play a big role in modifying the polymer electrolyte characteristics. Then coming to the polymer architecture, as I mentioned, you may have a polyethylene oxide, which is a homopolymer, or you can have a copolymer of PEO plus methyl methacrylate, which is a PEO PMMA polymer, which could be a random polymer, which could be an alternate copolymer, block copolymer, PEO block and PMMA block, or polystyrene block, etc., or a tri-block. Or you have a chain which is a polymethacrylate, and you can have a branching or pendant functional group, which is an ethylene oxide chain or other kind of polymer chains. Or even you can have cross-linked thermoset network. And most of my work, research work for the last 15 years, were focused on cross-linked polymer electrolytes. What are the advantages you can get, for example, for block copolymers? So you can see one of the examples are PEO, PPO, or PVDF HFP, or PEO PMMA. You can really tune, for example, if you can see here on the left-hand side, bottom of the side, you have a block copolymer which has a part A and part B. By changing the chemistry of part A or part B, or by changing its length or its processing conditions or its molecular weight of A and B, you can get a different kind of morphologies in the polymer matrix, or different kind of phase separations in the system, whether it can be sphere, cylindric, or a layered structure. As you can see on the right-hand side, where you have polyisoprene, polystyrene, and PEO. Here, PEO can be an lithium ion conducting phase, where PEI and polystyrene can give you mechanical strength for the membrane. So by combining this in right proportions, you can channelize lithium through this ion conducting area, which can contribute further for the development of polymer electrolyte and its mechanical properties. And as I mentioned, a polymer electrolyte is a mixture of polymer plus salt. From the salt side, you can have, in the previous, historically, most of the studies were carried out on TFSI-based system, for example, FSI or lithium TFSI based system, along with some perchlorate or LiBF4. But today we have a wide variety of salt systems are available, which are really helpful in modifying the polymer electrolyte system, whether it is a symmetric anion or asymmetric anion or a mix of anion. And historically, from the 1970s, 80s, most of the work, maybe more than 10,000 literature are available using only one type of polymer, one type of salt. But we can use different kind of polymer, different morphologies, different chemical structures, etc., along with the different multi-salt system. Instead of using single salt system, we can go for multi-salt system, where we can modify the properties. Besides, but we should take care that whatever the salt we develop, it should be soluble in the polymer matrix. It is pure. it should have a good ionic conductivity, it should be thermally stable, it should be produced easily, and cost, which is an important parameter. Even if you develop a battery, even if you develop a salt which is not so cheap, then it is not going to be realized in the market. Then it is of no use. So the cost is also another important parameter when you develop these kind of things. Then, as I mentioned again, there is a polymer plus salt, which is you can call as neutral polymer matrix, which is a PO along with this one. But the newer developments is to improve the lithium-ion conductivity and improve the percentage of lithium ions that is transferred within the polymer matrix, which is called a polyelectrolytes, in which the polymer backbone can bear a charge. Either it is a positive charge in the case of cationic polyelectrolyte, or an anionic polymer electrolyte in which the backbone is with a negatively charged. And especially in the case of anionic polymer electrolyte, when the positive charge is lithium ion, the only species that is moving in a polymer matrix is lithium ion. This lithium ion can move within the electrolyte where the anions are mostly immobile. This is one of the reasons that you can get a very high transport number, which is very close to 1, where only lithium ions are moved. Whereas in the case of PO-LiTFSI, you have cation and anion, both are mobilized. So maybe only 20% of cation is mobile and 80% of anion is mobile. From that system, a simple system, to only 100% lithium is mobile and anion is immobile, is something where we can improve the overall ion dynamics within the polymer electrolyte system. Then there is polymer composite electrolyte. For example, in the beginning, in the 80s and 90s, there were attempts to increase the mechanical properties and increase the amorphous nature of the polymer by adding nanoparticles, either it is alumina, silicon dioxide, etc., with the lithium salt. These are cheap and this can improve the crystallinity. They can reduce the crystallinity and they can trap the impurity, and this can also form a better interface with the lithium. So the lithium interface and resist the dendrite. But now from the development and the further technologies, we can produce small scale lithium ion conducting ceramic particles, which can be also used as a ceramic filler, which lead to a new kind of polymer electrolyte system, which is called a hybrid electrolyte system, where the polymer can conduct along with the ceramic. Again, even in this case also, you can produce ceramic in polymer, in which polymer is the major part, ceramics are small part, or polymer in ceramic, where ceramic is the major part, polymer is the less part. According to that, you can even have a different conductivity. For example, in the case of LLZO-PO, you have polymer that contributes mostly for the ionic conductivity, whereas in the case of LLZO in higher quantity, you have LLZO that contributes mostly to the ionic conduction. So from polymer matrix, salt, polymer architecture, etc., you can develop polymer electrolytes. And from the polymer reaction point of view, if you look, there are mostly used polymerization, free radical polymerization. Especially in my case, I have been focused much on photopolymerization. However, there are other polymerizations like click reactions, atom transfer, HERP, atom transfer radical polymerization, or RAF techniques, which you can use and you can engineer a polymer chain, whether it is a block copolymer or monopolymer, or it's a different morphologies. And mostly unsaturated monomers are used. Then there is another polymerization, which is ionic polymerization, which is very leastly used, where you can use methyl methacrylate or even glycidyl ether epoxides. And these epoxides even can be polymerized using lithium salt itself. So you don't need to use additional materials as an initiator to continue the polymerization. So you reduce the complexity of the formulation by even using lithium salt itself as an initiator. Then there is a classical condensation reactions where you can use polyurethane, you can produce polyesters, polyurethane, etc. Even those materials can be explored further, or you can use in situ electropolymerization, other kind of technique to modify the electrode surface. And coming more to my work and my experience, it is UV photopolymerization, and to produce cross-linked polymer electrolytes, we use monomers, initiators, which is a polymerization system, and then salt and additives. And mostly monomers, we use acrylates, methacrylates, or allyl ethers or allyl carbonates, etc. So in a simple system, we have photoinitiator, monomer, etc. We can mix these things together. We can UV irradiate it to produce a cross-link network. So initiator is there, which absorb UV light, which will produce radicals. These radicals can react with unsaturated bond here, for example, double bond, and then it can continuously propagate this reaction to form a cross-link network. Now, I don't know how much time left for me, maybe not much. So
maybe please 5 minutes.
Yeah. So
thank you.
I will give only one example of one of my recent work where if you compare with a polymer electrolyte, you have a polymer electrolyte where you have a lithium salt and polymer. But in this case, we are using multiple salt systems or multi-salt chemistry, because you can really fine tune the same polymer matrix with the multiple salt to get a much improved product. It has been leastly applied. It is most successfully applied in liquid electrolyte, but very few attempts have been made in the solid state system or polymer electrolyte. So we want to explore this idea and see how it is going to influence. And it was surprising how a single and second salt or third salt is influencing the overall electrochemistry of the polymer electrolyte. For example, here you will see that you have a cross monomer, which is PEG-DAE, which is a oligomer, which can be polymerized by UV radiation with a dual salt system, and you can get a very nice cross-link system. Just by adding the second salt, whether it is applicable to different systems, for example, lithium perchlorate, DFOB, LiBF4, LiTFSI, etc., you can increase the ionic conductivity. And moreover, you can increase the ion transport, the transference number, even 3 times increase as compared to a single system. Besides, when you mix and match these different anion systems, you can increase the conductivity, you can increase the salt concentration. For example, if you are using only TFSI, at certain level, you cannot increase further the TFSI addition, because it will not solubilize, or it will increase the viscosity. But keeping that viscosity or keeping the same concentration, you can, using a second salt, you can improve total lithium salt concentration also. And then you can play with the anion synergy, which kind of anions you use, 1, 2, or 3 different families of systems. You can combine this to have a better anion synergy to improve the interfacial property. And one of the interesting factor for us is that why the polymer electrolyte is improving all these ion dynamics within the system. We understood that the anions, what we are adding secondary or tertiary anions, this can act as a mediator, and this can improve the ion transport. So it is a mediation. It can act as a mediator between 2 polymer chains. So because of the coordination, it reduces for example, lithium is in a PO-based system, lithium is coordinated to PO. When it is coordinated more to the PO, it will stay there. It will not move because it needs higher energy to move. So it reduces the ionic conductivity. So when you are adding the second anion, this lithium is less coordinated with the PO and more coordinated partially with the anion. So this makes this gives the lithium a lower relaxation time. The relaxation time means that the amount of time that lithium is staying with that particular polymer chain or particular space. This is reduced drastically, and this anion can be a carrier or a mediator to transfer this. So because of this, we get increased ionic conductivity, improved transference number, improved diffusion coefficient, etc. Further, this can also improve because of the increase in transference number, the polarity or our voltage is lower here. The salt, the lithium, the membrane can go for longer time for lithium plating and stripping, as also Professor Ruffo mentioned, why it is important, why we should avoid short circuits, etc. And even we can go for higher energy deposition. For example, we can go to 1.5 milliampere hour per centimeter square instead of the classic 0.1 or 0.2 mAh without the dendritic formation. So all this we achieve within the same molecular system just by adding another salt. And most importantly, when you cycle these kind of systems against lithium iron phosphate or other kind of cathodes, you will see that there is at least 5 times increase in the specific capacity at a higher C rate. Because C rate is important, because 1 C rate means that you charge for 1 hour and discharge for 1 hour. So when you have a car, you don't want to stay for 1 hour. Maybe you want to stay there for 10 minutes and you want to charge your battery. So this is where the C rate is important. And at a high C rate, when you use multiple salts, it can improve the specific capacity at least 5 times And even durability wise, even after 400 cycles, even you can get more than 95% of or 90% of capacity retention, and which is, if you compare with the single salt system, which is an 80% increase in specific capacity. So these are some of the basic ideas you can get even just by adding an extra salt. So then think about what you can do when you use different kind of morphologies, different kind of salt, its combination. Using the AI maybe is a good option in this case. And finally, this is the last slide. The polymer processing can do a bigger advancement. For example, you have a cathode, you have binders here, you have carbon particles, etc. When you add liquid electrolyte, it can go everywhere. This means that your electrolytes are happy and your active materials are happy, and lithium is reached everywhere. But when lithium ion is replaced with the polymer electrolyte, when we make it as a sandwich system, only the surface, the material on the surface, active material on the surface is happy, whereas or they are only in contact with the polymer electrolyte, whereas the other bulk systems cannot be completely in contact with the lithium ions. This means that lithium can only transfer through the active materials. This creates this slow down the reaction kinetics. This slow down the this will reduce the active material utilization. This will reduce the performance at a higher C rate. So it is important when we think about solid polymer electrolyte to go for in situ based systems where you deposit the polymer electrolyte also in the bulk of the electrolyte and use more solvent-free techniques or other kind of fast processing to improve the battery performance. And besides, it is also important to look at the interfaces like solid electrolyte interface at the lithium metal surface or cathode electrolyte interface at the cathode surface. So even when you use thinner fabrications and in situ processing, you can even fine tune these interfaces and you can get a system which is a multi-layer system. So instead of going for a one polymer, one salt system, you can develop multi-layers of electrolytes with a different thickness. And these electrolytes can be engineered in such a way that you can have, it can be target specific. Maybe you will have an electrolyte that is more close to the cathode, so it will be stable against cathode. Whereas it may not be stable against anode, but it is stable against cathode. Then you develop another layer, which is a CI layer, which is again a polymer electrolyte, which can have a very good interaction with the lithium metal. And then a center layer, which can have another property. So you can really tune according to your need, how you want to design your polymer. So to conclude, I would say that in the case of polymer electrolytes, even though it has been there since last 40 years or 45 years, there are a lot of opportunities, especially by the introduction of lithium metal or other metal battery systems or metal-free battery system or anode-free battery system. We can do a lot of things, especially by controlling the polymer morphology, by using new salt chemistries, multiple polymer backbone systems, or additive chemistry, which is very well used and very well established in liquid electrolyte system, which is leastly explored in polymer electrolytes. This additive chemistry can may do wonders even for optimizing the polymer electrolyte system. Then from the engineering side, you can have multi-layer system, each layer tailored according to its requirements. You can make these kind of artificial interfaces, which will give you much advancements compared to the previous generations of polymer electrolytes. So with this perspective, I would like to thank the organizing committee for giving me, for inviting me again to Tahir and Hicks committee or university for the university members. And thank you very much. And also my group members and my head, who is Professor Dr. Martin Minder, and my group members Aisha Moore and Vidyanand, etc. And also funding from BMBF project. So thank you.
Okay, thank you, Jijeesh. Thank you very much. Such an informative talk, and particularly for those who are working with the polymer science here, so students, they were very much excited. So they have a couple of questions, but I think I will share these questions later through email. Just one question probably. Yeah. Like particularly in this hybrid system. So when you mix the inorganic materials like ceramics,
Yeah.
So does the size of the ceramics particles or the inherent conductivity of this is the kind of a factor one must consider while making these hybrid materials, or it's not a big deal?
No,
Only
no,
polymer does the
yeah.
job.
Yeah, no, as I mentioned in this one depends on which kind of polymer composite you want to create. For example, in a polymer composite, for example, in this slide, you can see even if you add 5% of ceramic electrolyte, it is not going to conduct because the activation energy for that conduction is higher. And if the surrounding area has a lower activation energy for ionic conduction, it will conduct through that part. So you have to really balance the concentration, and you want to see which part of your composite you want to conduct. That is the first point. Second point is the size. If you have when you reduce the size of the particles, there's an issue with the grain boundary. At the same time, when you increase the size, then for example, if you have a particle size ceramic material that has a size of 50 micrometer or 80 micrometer, then it becomes difficult for the processing of the electrolyte and making
that diffusion is the limit.
Yeah. So uniformity. So in that case, you need more homogeneous powders with a smaller size, but you should guarantee that the interfaces are better tuned, so that you can have a better lithium mobility through the ceramics if your target is on ceramic electrolyte.
Okay, thank you very much, Jijeesh. Thank you. So we have Professor Michael again here, Professor Ruffo, Professor, I like Dr. Jijeesh, and Dr. Shahzada also. So first of all, on behalf of King Fahd University for Petroleum and Minerals, Chemistry Department, KFUPM Institute for Knowledge Exchange, KICS. So, and all on the behalf of audience, I would like to thank you all for your time, for your active participation, and all this, sharing your experiences and enlightening and making this forum successful. So first of all, just for conclusive remarks, I would request Professor Grätzel. So could you please just, I know that I have already taken a lot of time, but the students are very much eager to know that if they want to work in this area of sustainable energy, so what they have to, consider while designing their projects. It could be like, for example, they have to target the basic chemistry fundamentals in their proposals, or they have to target to achieve high efficiency and some technology. So they just want to hear from you, like what should they, like basic science, or probably more on the application point of view.
Well, I think we all should have a trade. In other words, we should be firm on at least in one area of science. Like somebody is an organic chemist, that's fine. He could help a lot with the preparation of molecules. You have seen the variety of materials used in the Perovskite and dye-sensitized solar cells. Then comes the physicist. He also very, very useful for device characterization and analysis, and material scientists. So, but one thing is for sure, you should go into profoundness. You have to master at least for one trade. If somebody is superficial and knows everything, but not really deeply, that's not so useful. If you know one field well and you're solid, then we can always train. For example, we train students to make solar cells. That's not difficult, okay? And but one area of science you should be firm.
Okay, thank you very much. Very well received. So the same like Professor Ruffo. So particularly in the sustainable energy devices for storage purpose. So what would you like to suggest to students if they want to work here in this area? So what will be the...
It's a very interdisciplinary area right now. And as already mentioned in my presentation, we are discovering again the importance of interfaces and the stability of materials against each other. For example, in the last answer of Jijeesh, he was speaking about, in the last slide, he was speaking about how the polymer, it's wetting particles. Or another field, we are discovering right now what is going on the positive material at high voltage, how the electrolytes decompose there. So this is a completely new fields of research, and you can make a lot of useful stuff here. So not just focus specifically for the battery world, not just focus in capacity, in bike properties, but look at the interfaces, which is fundamental to improve the future device, the devices of the future.
Okay, thank you very much. So, Dr. Shahzada Ahmad, so please sorry, Dr. Ruffo, if you have some further.
The future is electric.
Future is electric. Yeah, thank you. Thank you very much. So, of course, this is the message from Dr. Shahzada already. So, in the talk. So, Dr. Shahzada, so just please, could you summarize your thoughts on this particular topic, like how important is particularly, chemistry? Of course, Professor Michael Grätzel has already very beautifully said that there should be, one area that should be mastered, by someone who wants to work. And of course, the rest, they will be also, contributing. We cannot claim chemistry is, like everything, but the role of chemistry, particularly in this sustainable energy. So could you please tell students a little bit about the role of chemistry? I'm sorry, can you hear me, Dr. Shahzada?
Maybe he's frozen, maybe.
Yeah, maybe it looks like his computer is
Frozen, yeah.
Yeah, it's frozen, yeah, we can see. So I think then this question I will put forward to Professor Michael Grätzel, like I was asking from Dr. Shahzada, the role of chemistry particularly.
The role of chemistry is key. I mean, we have, I think we are very fortunate to have the education in chemistry that allows us to understand what is, for example, what is going on in nature, the natural photosynthesis, and learn from it. So that's why I studied chemistry, because I tried to understand the processes that are life-sustaining, like respiration and photosynthesis. And so, yeah, we are very fortunate. And the laws of physics are okay, but they are limited. The chemistry has no limits. You can always invent new molecules and new reactions. And so it's a very fertile area. And I think the environmental problems that needs really mostly chemistry to be solved.
Okay, thank you very much. Thanks a lot. So I'm sure like it will be a lot of motivation for the students, and it's rightly said. So I think the same question I will forward to Dr. Nair, like Jijeesh. So please, would you like to say something to students if they want to come up, for these energy storage devices? So what factors, based on your experience, they should always, be considering to master this area?
I would say whatever the energy you produce, you should store it. So energy storage is going to play a big role in the coming years, whether it is liquid based, electrolyte based, or solid electrolyte based. So somebody already wrote in the comment like, yeah, from my opinion, so future is going to be solid, and it is going to be electric as well. So it is going to be electric, and it will be solid as well.
Okay.
So from my perspective, I studied polymer chemistry, bachelor, master's, also my PhD in polymer chemistry. I work on polymer electrolytes. So I focused on the polymer science field. But today what I see is that even for us, while we do research, AI-based systems are playing a big role. AI, the data science is going to play a big role. So in future, I also feel like even if you are whatever the field of science you excel, you should also understand how data is managed, how at least to know one language, for example, whether it is today it is Python, tomorrow it is C++ or whatever it is, it will be part of our system. When we talk to other kind of field, whether it is physicist or physical chemist or theoretical chemist, we are learning a lot. So collaborations and talking to other people from other field is going to be also another key to explore your field as well as the other fields, in my opinion.
Thank you. So maybe Dr. Shahzada, already sorry we could not hear you before. There was also one question actually from one of the audience, and that was how long you think it will take us, for example, to replace silicon-based solar cell with perovskites?
Yeah, this is a very tricky and challenging to ask, but we are committed to adapt carbon neutrality. Europe is committed by 2050, even before that one. So this
Sorry, we cannot hear you, Dr. Shahzada. I'm sorry, we have still sound problem. We cannot hear you.
Can I say something?
Yes, please. This will be
I
approached.
think the question is not to replace. The question is to add on to silicon so that we can master the challenges. We need silicon, we need everything.
We need everything. Okay. Thank you. So I think once more, if I just remind myself to have a take-home message for today, and also this is the take-home message for students and for everyone working in this area, is something that if we, all through these talks, what we have seen, the major challenges, those are related with the stabilities, our efficiencies, our interfaces, our cost. So I think through proper understanding of the chemistry, small molecules, or big molecules, inorganic, organic, physical aspects, if we are able to understand those, so probably we can solve these problems. So with this, I would like to extend one more time my hearty thanks to all of you. Thank you very much for your time. I know that how busy time you have, for example, and particularly in this part of the year when proposals probably will be coming soon to be submitted. So thank you very much for your time, and I thank you all. And I wish you a very safe and healthy life ahead. Thank you.
Thank you, and thank you for
Thank you, Tahir.
Thank you very much.
Thank you all.
Thank you, Jijeesh. Thank you, Professor Ruffo. Thank you.